G'day guys, Socket here. In today's tutorial we're going to cover the topic of speaker specifications. Things like FS and Xmax and QTS, stuff like that. Things that you've probably heard of before but might not be too sure exactly what they mean. Now this is a pretty complicated topic and so this tutorial is going to be pretty long. Maybe my longest tutorial ever. But look, don't worry, I'm going to break it up into smaller individual videos so that you can take your time watching it and don't have to watch a whole 3-hour tutorial all at once, and also to make things much easier to find. So let's dive into today's topic, speaker specifications. Okay, so first of all I'm going to do a quick summary or a quick introduction and summarize up all of these speaker specification parameter things. So if you're looking for a particular term and a particular definition, you don't have to trawl all the way through the tutorial to find it, okay? But just really quickly, a speaker is made up of various components that are put together as a motor driver or a speaker driver, the suspension and the cone. And as I said, I'll go through all this detail later in the tutorial. But the way a speaker works is the motor drives the cone up and down, the cone moves the air and creates sound, right? Pretty simple. But you have probably, when you've been researching speakers and looking at what you're going to buy, you'll probably have pulled up the speaker technical specification sheet, and typically you'll find some dimensions about the speaker, something about how the speaker response plays, its impedance curve, and then a bunch of technical details, right, including these things that are called the THIELE small parameters, right? Now, why are they called THIELE small parameters? Because there was a couple of Aussie researchers who go by the name of THIELE and Small, who did research on speaker box designs and stuff like that, and how to measure different speaker components, back in the 60s. In fact, this Albert Neville THIELE was the initial researcher that did a lot of the scientific research on speaker and box design, and then an American scientist came along a little bit later, a guy called Richard Small, who moved to Australia, and he developed a lot of the actual techniques to do the measurements themselves. And so together, both working at the Sydney University, they developed a number of scientific papers that today we call referred to as the THIELE small parameters. And these things are really helpful in allowing us to compare the strength of different speaker motors, how different speakers perform in terms of loudness and quality, and the different characteristics about the suspension and other parts of the speaker that when they combined as a whole unit will tell us a lot about how a particular speaker will perform. So that's a quick introduction to the topic of speaker specifications, but what I'd like to do next is take you through some of the THIELE small parameters and speaker specs that we're going to be examining in detail during this tutorial. Now, I've already made a summary, standalone summary tutorial on these parameters. I'll put the link to that down below. So let's get started on the motor. So the main parameter or THIELE small parameter around motor is motor strength, which has a shorthand of BL. Motor strength is basically how much force the speaker motor can apply to the cone for a given amount of power. The other parameters around the speaker motor are things to do with the voice coil, so its physical dimensions, its length, its height, its diameter, how many layers of wire it has on it. The magnetic gap, so the magnetic, the amount of magnetic force and the magnetic gap size that the speaker voice coil moves up and down in, and then a bunch of electrical parameters around things like voice coil resistance and inductance, impedance, and back electromagnetic force. Excuse me. Then if we move on to the next one, which is the cone, really what we're looking at there is how much air the cone can move. So displacement capacity, which is VD, or the cone area, surface area, and things like the weight of the cone, or what we call the moving mass, the cone and the suspension, because that has a bearing on the amount of inertia that the speaker has, and those types of things. So we have some measures around total moving mass and what we call mechanical moving mass. Then we have some parameters around the suspension. This is mainly around how soft or stiff the suspension is. So we have what we call suspension compliance, which is how soft it is, and its inverse parameter, which is suspension stiffness, or KMS. There's also a measure called VAS, which is used for calculating speaker boxes, and that is basically how much air trapped in a box would be as springy as the suspension on your speaker. And then of course we have a suspension losses measure, which is about how much the suspension loses in terms of energy, in terms of the flex and friction involved in the suspension parts. If we move on to the speaker itself, all the parameters that relate to the speaker operating as a whole as opposed to their independent components, we have three main ones are sensitivity, efficiency, and power handling. So sensitivity is basically how much loudness or decibels that the speaker will produce for a certain amount of energy. Efficiency is how well it turns power into sound energy, and power handling is in watts, is about how much power or heat that the speaker can handle. The other measurements related to the speaker include movement or excursion, so the amount of up and down movement that a speaker can make and what those limits are, including Xmax. What we call the resonance, so how the speaker oscillates at its natural resonant frequency, so that's Fs, or if it's in a box it's called FC, and if it's in a ported box it's called FP. And it will cover what resonant frequency is and all of that stuff, as I said, later in the tutorial. And then of course there is dampening, the terms QTS or QTC if it's in a box. Dampening is about how quickly that oscillation of the speaker comes to rest, or and so QTS is a measure of its dampening, and it's made up of its electrical and mechanical dampening. As I said, the terms are different depending on whether it's in free air or a box. Well, on the topic of boxes, the VB is the internal box volume, so you might see on a technical sheet the term recommended box volume, and it'll have VB equals so many cubic feet or litres. And finally, a measure called efficiency bandwidth product, EBP, which is a calculation that you can use to work out whether a speaker should work in a ported or sealed box or in free air. So these are all the types of measurements and terms that we're going to look at during the tutorial, plus a bunch of others as we go along. So we've got a lot to get through. So let's go dive on in and start taking a look at our first topic, which is how does a speaker work? Well, there are lots of types of different speakers, but I'm going to try to keep things simple and just ignore the exotic types like air motion transformers or ribbon speakers and compression horns and stuff, and just focus on the garden variety everyday moving coil speakers that we know and love, because they make up 99.99% of all the speakers that we have installed in our car audio systems, right? Now, a moving coil speaker is made up of several different bits. Includes the dust cap, the cone, the voice coil, the spider, which is part of the suspension, the basket that holds everything together, the top plate, magnet, and back plate, which is often called a bottom plate, which has a piece that an extension that sticks out called the pole piece. So this is all one piece of metal, right? And if you squash them all together, you get the typical moving coil speaker that we are all kind of familiar with. Now, the speaker moves up and down when you apply electrical energy to the voice coil because the voice coil is interacting with the fixed magnet, and it causes the coil to move back and forth. And because it's connected to the cone, it moves the cone as well, which makes pressure waves, which turns out we can hear as sound, right? So let's go take a closer look at the parts that make up the speaker, starting with the speaker basket. Now, there's not a lot to say about the basket. It's essentially the structure that holds all of the bits of the speaker together. It does have a role in airflow and ventilation. That's why there's usually big cutout sections to to the basket itself. But other than that, there's not much more to say. The next part of the speaker is the driver motor. Now, it's called a driver motor because it's like, well, it is an electrical motor. It works using a coil of wire and electromagnetic interaction between two magnets to create motion. But instead of spinning around on a shaft like a typical electric motor, this electric motor pushes back and forth, right? But that's where the name comes from. The motor is made up of the magnet, the top plate, bottom plate, and a voice coil. Now, the magnet is a fixed magnet. It's donut shaped and sits at the bottom of the speaker. We're all kind of familiar with speaker magnets. And then on sandwiching the magnet is the top plate and the bottom plate. So these are two bits of metal. The top plate is kind of like a donut. The bottom plate is also like a donut, but with this extended pole piece in the middle. Basically the role of the top and bottom plates is to take the magnetic field and create a magnetic circuit. And the shape of the top and the bottom plate creates a very narrow gap, which we call the magnetic gap. And we'll talk about that a little bit later. The voice coil is a cylinder of wire wrapped around a cylinder called a former. So the former gives the voice coil a structure, something to sort of wrap around. The voice coil is the thing which we pass the audio signal through, and when we pass that current through the voice coil, the voice coil becomes like an electromagnetic or electromagnet, right? And creates an electromagnetic field that can interact with the fixed magnet. And depending on the direction of the current or its polarity, the voice coil will either be pushed forward or back. So that's the driver motor. The driver motor, or the ends of the voice coil leads are connected to your terminals where you connect your speaker leads, speaker wires, I should say, via these things called tinsel leads, right? The tinsel leads are kind of dangle, or they're kind of corrugated, like you can see in this illustration, because the voice coil is the cone is going to move, and the voice coil is going to move, so the tinsel leads need to be able to move and flex as well, and that's why they're either corrugated or longer than you would normally think, right? But if they were fixed, you'd find that the tinsel lead would break. And in fact, it's a common failure point in speakers where you have a tinsel lead will break, and of course the speaker won't play anymore because the electrical connection is now broken. Alright, the next bit we want to look at is the speaker cone. It is made up of the cone, the surround, and the dust cap. So the cone is this bit in the middle. It's the part that is attached to the voice coil, and it's the part that actually creates the sound, right, or the pressure waves by moving up and down and creating those sound pressure waves in the air, which creates the sound that we can kind of hear. The other part of the cone is the surround, right? It's the outer edge of the cone, and it's you can see it's got an arch shape cross section. It comes in, sometimes there's one sort of arch, sometimes it's 2, sometimes it's all fluted, different types of surrounds, but they all do the same thing, and that's to connect the cone to the basket and to allow the cone to sort of move and freely. So it's the surround that actually allows the cone to kind of flex. And then we have the dust cap. As the name suggests, it's there to stop dust and dirt and things getting into the voice coil, or the gap between the voice coil and the bottom plate. So the voice coil doesn't get jammed or anything like that. So that's what a dust cap is for. And then we move on to the speaker suspension, which is made up of the spider and the surround. Now, the surround we just had a quick look at, that's the part that connects the top of the cone to the basket and allows the cone to move freely. And the spider is this fluted material piece at the bottom that connects the bottom of the cone to the basket. And so between the two of them, they make up the suspension. And it's called a suspension because it acts like the spring or the shock absorbers in your car or the springs on a trampoline. They allow the cone to move up and down, they move along with it, and they provide a level of force against the the movement of the cone itself. So they have a role in allowing the moving parts of the speaker to move, but they also have a role in controlling that movement and keeping the voice coil properly aligned and controlled in the magnetic gap. So that's the way a moving coil speaker is constructed and all the parts that make it up. But how does the speaker actually produce sound by passing electricity through it? Now, this is a topic I found really hard to get my head around when I first started with car audio. And so I'm going to explain how that works next. Okay, so let's say we have an amplifier with some speaker wires and we connect that to a speaker via the speaker terminals, and now we have an electric circuit, right? But if we zoom in to that speaker, it's made up of a voice coil, which are connected to the amplifier via the terminals and the tinsel leads. We have a permanent or a fixed magnet that's surrounding the voice coil, and then of course we have the cone that's connected to the voice coil. So as the voice coil moves, the cone moves back and forward, right? But if we have the amplifier turned off and there's no electricity flowing or anything like that, then of course everything's just sitting there, the speaker's not moving, not making any sound or anything like that. So when we turn the amplifier on, however, the amplifier generates electrical power, and that power, if it's all connected to the amplifier properly and it's when it makes a circuit, the power's going to flow around the circuit through the voice coil and and all that type of stuff, right? And that's all great, but there are two terms that we need to just talk about quickly to understand how an amplifier actually works, right? And those two terms are voltage and current. So voltage is, you can think about it like water pressure, right? Or it's electrical pressure, for want of a better term, right? So if this was, water in a pipe, you can think about voltage as, the water pressure, pushing the water around the circuit, right? And you can think of the current as how quickly it's flowing around, or the flow rate that going around the circuit. In fact, the term current comes back to the old days when they were getting their head around how electricity works, and it's like the current in a river, right? How fast things are flowing. You can kind of remember it kind of a bit like that, right? If voltage is the amount of electrical pressure and current is how fast things are flowing, you can, you think about this like water in a pipe. If you increase the voltage, it will force more water through, or it'll make the current faster, right? So yeah, increase in voltage, you get a stronger current. And this, similarly, if you reduce the voltage or the pressure, then you get less current flow. the flow will slow down, right? So voltage will dictate the amount of current that's flowing, around a circuit. The other thing that you can do with voltage, though, is you can have positive or negative voltages, right? So the good thing about voltage is that if you, for example, flip it to, I don't know, a negative voltage, then all of a sudden the current will start flowing in this direction, opposite to the way we were before. And if you flip the polarity back, then the current will flow in this direction. And that's really handy because what it means is by changing the polarity of the voltage in your speaker wires as they're attached to the cone, we can change the direction of the current flowing through the voice coil. Right, now, why is that important? Because when you put current through a voice coil, it creates a electromagnetic field, and that electromagnetic field interacts with the fixed magnetic field and causes the voice coil to move. Right, so if you apply a negative polarity or negative voltage to the voice coil, it will cause the voice coil to pull back. And because the cone is attached to the voice coil, it will cause the cone of the speaker to move back as well. And then if you reverse the polarity and you apply a positive voltage to the voice coil, the opposite will happen. The voice coil will move forward, and of course, because the cone's attached to the voice coil, that will move forward as well, right? And of course, the strength of the voltage, so if you have it at 1 volts versus 3 volts, 3 volts will cause the voice coil to move much stronger than 1 volt, right? So using this neat little trick, this polarity flipping trick, this is where the audio signal from an amplifier comes in. So when you look at an audio signal like something like this, right, peaks and dips and all of this type of stuff, this is the audio signal. The size of the peaks relate to how strong the signal is. So loud, if you want things loud, you've got taller peaks. You want things soft, you have smaller peaks. And of course, things above the line are positive voltages, and things below the lines are negative voltages. So you can kind of, almost like a record, right? You can have a very small positive voltage and then a negative voltage, small positive, small negative, a large positive voltage and large negative voltage, right? And that's what the amplifier is sending down the speaker wires as an audio signal, right? Now what this means is you can change the direction of the current, depending on whether that audio signal is a negative voltage or a positive voltage, and you can change the strength of the signal depending on whether it's a high volt, say 3 volts versus half a volt, right? And that's essentially what an audio signal is. It's just a big string of voltage values which are either positive or negative. And because they're sort of seesawing back and forth, right, you can see up, down, and right, positive, negative, this is what's making the cone, the direction of current is flipping, back and forth, and pulling the cone in and out, and the strength of which it pulls the cone in and out, and of course that relates to the loudness that you will hear, is determined by the size of the peaks or the voltage of the size of the voltage that is being applied at the time. And that's basically how a speaker makes music, right? Now, that's all great. And in a perfect world, that's all we'd need to worry about, because, there would be no resistance or anything like that, and electricity could flow back and forward and change direction instantaneously, and and all of that stuff. But in the real world, things have resistances. As electricity flows through a material like a wire or a voice coil, there is a certain amount of resistance, and so we need to talk about some things called inductance and impedance, and how that sort of affects the way the amplifier and the speaker works. So I'm going to start with the term inductance. So inductance is basically the opposition to a change in the direction of current. So if you can think about it like water flowing in a pipe, if you suddenly get the water in a pipe to suddenly change direction and go in the opposite way, it won't happen instantaneously, right? It's going to slow down and slosh about and then sort of move in the opposite direction. And inductance works in the same way, right? It's the resistance to the change in the current's direction. So the more often you change the direction of the current, the more resistance there will be, right? Or I should say, the stronger the inductance effect becomes. So for example, let's take 100 hertz per 100 hertz frequency. That means that you're going to change direction 100 times per second, right? And if you're playing 8,000 hertz, then that's 8,000 times a second, right? So, 8,000 changes per second is a lot more than 100 changes per second. So the inductance for high frequencies is much higher than low frequencies, and so inductance increases with frequency, right? And that's why when you look at impedance curves and things, because impedance includes inductance, that's why you'll see impedance curves when you look at speaker technical sheets and things. You'll see that there's a big rise as you in the impedance as you go up in the frequency. All right, so with inductance out of the way, we can now talk about impedance, because impedance is the overall resistance of the speaker to current flow. So it's kind of like how much the speaker limits current flow through the voice coil. And it's made up of a bunch of things. It's made up of the voice coil's electrical resistance. So it's RE. Now what we mean by that is, the voice coil is a certain thickness and a certain length, and the more wire you've got, the harder it is for electricity to move through it or be pushed through it. So that doesn't change. The voice coil resistance is fixed. That's one part that makes up the the impedance. Inductance is the second part that makes up impedance. We just talked about what that was. And then we have something called back EMF, which we'll get into later, but that's basically a force caused by by the voice coil moving up and down in the magnet and acting like excuse me, a generator, and a couple of other things. But because impedance includes inductance, it means that it also changes with frequency, right? There is the impedance resistance changes with frequency as well. It's not fixed like resistance. So you can think of impedance like a valve in a pipe, right? When the impedance is high, it means the valve is more closed and it's harder for current to flow through, or less current flows through the voice coil. And if impedance increases, that means that as an amplifier, you need to apply more voltage to get the same amount of current moving through the voice coil and maintain the same volume level coming out of the speaker, right? But if the impedance is low, it makes it easier for the current to flow through the speaker voice coil, so you need less voltage to maintain the same current and the same volume level, right? So you can think about impedance like a adjustable valve that's constantly sort of opening and closing, and the amount of that resistance or limit on current flow is constantly changing, right? But the good thing is that these fluctuations are not normally big enough for us to hear as big jumps in volume, right? Because loudness is more than just the amount of current flowing through the voice coil, right? So why is this all important? Well, because lower importance speakers like 2 ohm speakers allow more current to flow than, for example, a 4 ohm speaker when driven by the same voltage. So if your amplifier is stable at 2 ohms and can supply that extra current, then it can deliver more power to the speakers. So I'll give you an example. Let's say I have an amplifier that can supply 60 watts at 4 ohms, and I can supply 130 watts at 2 ohms, right? Now, if I'm running that power supply into a 2 ohm speaker, it means I can deliver 130 watts. If I'm running into a 4 ohm speaker, then I can only supply 60 watts. So if my amp can handle it, I can deliver more power into a 2 ohm speaker than I can a 4 ohm speaker, right? Because the 2 ohm speaker allows more current to flow through naturally, right? The trade-off is that because I'm now supplying more power to the speaker, a 2 ohm speaker, then amp has to work harder to provide that current and usually runs a lot hotter, right? And this is why it's important to match your speaker impedance to your amplifier, right? And make sure that you're, you're matching your amplifiers to the speakers with the correct impedance, right? To get the, the most out of them. Because generally, when you add more power to a speaker, they will be louder. All right, the next thing is to talk about is volume control and how that kind of works in this system now that we understand all the bits that are kind of moving together. And basically what happens is you will be getting, coming into your amplifier will be an input signal. Now that might be coming from your head unit or your phone or whatever you're using from a source, but you'll get that sort of audio wiggly pattern, whether it be in digital or analog. It will be feeding into your amp, right? And then the amplifier will be taking that signal and making a bigger copy of it, because it's an amplifier, that's what it does, and just makes a bigger copy of that and sends it out as, voltages, right? That drive the current that is flowing around the circuit. So if you turn up the volume on your phone or your head unit or whatever, this input signal will get bigger, and the amplifier will match it by increasing the output, making the output signal bigger, which means more voltage, which means more current. More current means more force on the voice coil, which means the cone will be pushed further and it'll make louder noise, right? So it's pretty simple. So the only thing that I guess I need to mention is bass frequencies, volume and bass. Bass doesn't mean that we have more impedance or things going on. The reason that we need more power when we're playing low bass is because we need to move a lot of air, right? A lot of air means more cone movement. To make the cone movement move more air, we need more power, right? Going through the speakers. Yeah, so that's how kind of volume control works. All right, finally there is watts. Talking about power, watts is a measure of power being delivered to the speakers, and you can think of it kind of like a tacho on your car. When you're playing low volumes, you're going to have low revs, and when you turn it up, you're going to have high revs, because you've got more watts going through your system. So, people think that I have a 100 watts speaker, it's always using 100 watts. That's not kind of the way it works, right? The way watts or power is calculated, or power is, so it's measured in watts, is it's a formula where volts times current equals how much power you're making, right? So if the amplifier is sending out so many volts and it's producing so many amps of current, you multiply the two and you get the number of watts that have been delivered to your speaker at a particular point in time, right? Now, because music is dynamic, and the signal's going up and down, and the amplifier's changing the voltage, and the current's always changing, and the impedance is always changing, and everything's changing. It means that the watts that are going to your speaker will be constantly changing, and as I said, will be a combination of the volts and currents at a particular point in time, right? So depending on how loud you've got your music turned up, this might be 20 watts, and then 5 seconds later it might be 32 watts, and then down to 14, whatever it is, right? So if you have a 100 watt speaker, what that means is that is the rating, or the power rating of the speaker. It's how many watts that speaker can handle safely before you exceed its thermal limits. So, if you push 100 watts into the speaker, fantastic, no worries at all. But, if you push 200 watts into that speaker, and you do that long enough, then you're essentially going to exceed the speaker's power handling capacity, and, it's going to overheat, catch in flames, burn down the car or whatever it's going to do, okay. So maybe I'm exaggerating, but that's, kind of how it works. All right, so to kind of summarize everything up, you have an input signal that is made up of, positive and negative aspects and peaks that reflect the sound or the music that you're playing, which comes through your head unit. That's amplified by and copied by your amplifier. That sends a series of voltages, positive and negative, to move the current direction of the current back and forward. It's the current that is moving through the voice coil that actually creates the force that moves the cone, but it's the voltage that kind of sets the direction and the strength of that current movement. But it's the physical current movement that moves the cone, not the voltages. The voltages is just the, for want of a better term, the signal. And of course the watts is the measure of the two at any particular point in time. The cone's moving back and forth and, playing music. Yeah, so that's kind of how it works. Okay, so now that we have a good understanding of volts and current and all of that stuff and how it works, we can now move on to taking a closer look at the different parts of the speaker and how they operate, and the parameters that manufacturers use to describe the performance and characteristics of these different speaker components. Things like motor strength or suspension compliance and stuff like that. And so we'll start with probably the most important part of the speaker, which is the driver motor. So let's go take a look at how that works. Okay, so we'll start off with the driver motor, which we touched on earlier when we were looking at the different speaker components and things like that. And as we mentioned before, all the driver motors have a permanent magnet or a fixed magnet. And like all magnets, they have a north and south pole, right? Now, the driver motor is actually made up of several parts. One is the top plate, one is the bottom plate, and this bottom plate has a shaft or a pole piece that extends up into the driver motor, and of course the magnet itself. And you can kind of see these bits easier in the in this diagram, right? Because it's exploded out. So here's the top piece, here's the bottom piece, bottom piece and the magnet, and this back plate sort of goes up through the holes and provides a shaft, for want of a better term, that the voice coil moves up and down on, right? Not really, because it doesn't touch, but you kind of get the idea. So the top and bottom plates sandwich the magnet, and they adopt the the north or south pole charge of the permanent magnet that they're adjacent to, right? So in this case, the top plate is touching the magnet on the north side, so it adopts like the north pole, and the south pole is sort of adopted by the bottom plate, right? So what we have here is a magnetic circuit, but it's not complete because there's a little gap here, right? And so the magnetic force has to kind of jump that gap, and depending on the engineering of the shape and and all that type of stuff, the magnetic force gets concentrated in this gap, and it's in this gap that the voice coil moves up and down, and we call this gap, surprisingly, the the magnetic gap, right? So let me talk a little bit about what the voice coil is. Right, so a voice coil is basically a cylinder of wire wrapped around a cylindrical piece of metal, piece of plastic called a former. And the former is just there to provide structure for the coil to be wrapped around, right? The ends of the voice coil are connected to the speaker terminals via little wires called tinsel leads. And it's the magnetic field of the fixed magnet, that's concentrated in this in this magnetic gap, where the voice coil and the fixed magnetic forces interact, and I'm trying to illustrate that with these little blue lines where the magnetic force has to jump from one pole to the other, right? So to kind of explain that a little bit better, if you can imagine, the fixed magnet is always got a magnetic charge, right? Just these yellow lines here. Whereas the voice coil is an electromagnetic magnet, right? So in other words, it only acts like a magnet when you pass current through it. When nothing's happening, when you're not applying any current through the speaker, it sits in what we call its resting position. So it's not pushed up, it's not pulled down, it's kind of in the middle, and it's being held in place by the speaker suspension. But there's no electricity going through the coil, so of course there's no magnetic force here, so these two things are not interacting, right? So the speaker cone is in its resting position, and you can push on the cone and make it go up and down with your hand, but it'll always return back to this neutral starting point. So it's a little bit like I guess sitting on a trampoline but without jumping. All right, but when we do apply a current to the voice coil, and it then creates an electromagnetic force and starts acting like a magnet, and then it will interact with the fixed magnetic field, right? So depending on which direction the current is going, and that's dictated by whether the voltage that's coming from the amplifier is positive or negative. But if it's negative, then the current will create a force that is attracted by the fixed magnetic field, right? And of course, the voice coil will move down or back. And then, of course, if you flip the polarity the other way, then the electric field switches polarity as well, and it gets repulsed or pushed away by the fixed magnetic field, and of course the voice coil and the cone of the speaker pushes forward, right? And so by alternating the polarity of the voltage, positive, negative, and changing the direction of the current, clockwise, anti-clockwise, you can get the speaker to move back and forth, right? Where these two magnetic fields are interacting. Sometimes they're attractive, sometimes they're repulsive, and that's how you get the cone to move back and forward, right? Now, if the current flow is very small, in other words, small voltages, then the cone won't move very much, and of course, the sound out of the speaker will be very quiet. If you have a lot of current passing through the voice coil and the voltages are very high, then the opposite is true. You'll get a lot of movement and therefore a lot of sound coming out of the speaker itself. So that's roughly how a speaker driver works. Okay, well, what are some of the things that influence the strength of a driver motor? And a lot of people would just come out and say, oh, it's the size of the magnet. And that's partially true, but it's not the entire story. So when you look at speaker magnets, they're basically made out of one of two types of material. There are what we call ferrite or ceramic ferrite magnets, usually made out of strontium ferrite or other compounds. And this is, the common everyday, ferrite magnets that are found in most car audio speakers. Very common, it's inexpensive, generally heavier and not as magnetically dense as neodymium, which is really hard to say. I'm just going to call them neomagnets from now on. But neomagnets are stronger, lighter, more compact, and therefore more expensive than ferrite magnets. And you tend to find neomagnets used in tweeters or where speakers where weight and space is important, such as slimline subs and things like that. Because they're stronger magnetically, so you can have a smaller speaker to produce the same level of magnetic force as the equivalent ferrite magnet, right? So when you're looking on your technical sheets, it'll have magnetic material for the woofer or the tweeter in this case, and you'll see ferrite or strontium ferrite or ceramic ferrite or some term like that. So sometimes the marketing people put these extra terms on to make them sound fancier, but it's all the same stuff. Or you might find, it's a neo magnet, and they list neo here, or double neo, or neo plated, or whatever. These different terms, for the same things, but you can tell what type of magnet your speaker has. Now, that doesn't necessarily mean that a neo magnet is always better. Sometimes speaker manufacturers use neo magnets when they don't really need to use them, because consumers think that neo magnets are somehow better and make better sound. Like I said, they're just two different types of magnets with two different levels of magnetic concentration, for want of a better term, right? So neo magnet does not automatically mean that the motor is stronger. It depends very much on the whole motor drive motor design, so don't be fooled by the fact that it's got a neo magnet or that you've got super big magnets on there. Speakers with big magnets do not automatically mean that they're going to have big output, right? Because often some of that stuff that looks like a magnet is actually, pieces for cooling, or, parts of the bottom plate or top plate. Because once again, speaker manufacturers know that consumers think, big magnets are better, right? So just be careful when you're sort of looking at magnets on your speakers. Right, the second thing that influences motor strength is what we call magnetic gap and flux density. So this has all got to do with, the strength of the magnetic interaction between the fixed magnet and the voice coil, right? And and as we talked about earlier, the bottom pieces of the driver motor and the magnet, form this magnetic circuit, and they're engineered to create a gap for the voice coil to slide up and down in. And it's this gap where the magnetism is most concentrated and provides the force that actually moves the voice coil and the interacting cone. So we actually can measure this magnetic strength in this magnetic gap, and we use a term called flux density. The shorthand for that is B, and it's the strength of the magnetic field in this gap. So you can look on the spec sheets and you can sort of see, whether it's a weak flux density or a high flux density, but that's certainly one of the measures, right? Generally, the higher the flux density, the more push-pull force a driver motor will have, but once again, it's not the entire story. The second part that influences this is the size of the gap, or what we call the gap height. Clearly, if the bigger the height, the more a magnetic interaction can occur between the voice coil and the magnet, right? So gap height on the technical sheets will be shorthanded as G, and it's the distance between the bottom of the gap and the top of the gap in the driver motor. So when you look on the technical sheets, you'll find something like this: HE magnetic gap height of 3 millimeters, flux density of 2.36, which is pretty strong. It's that's how you find out those parameters. The next part, which is kind of related to the magnetic gap and flux density, is what we call the voice coil length in gap. So the voice coil is this winding of coil wire around the former, and of course the more wire that you have in this magnetic gap, the stronger the electromagnetic force from the voice coil and the fixed magnet interaction will be, right? And the more wire you can have in this gap, the stronger the motor can push and pull the cone, right? So here's the voice coil, here's the gap. The more wire I can get in there, the more force I can generate, right? So now we have some measures that we can actually combine together to be able to compare different driver motors. So the first measurement is the flux density, how strong the magnetic force is in the gap. The second measure is how much, or the voice coil length, in other words, the effective length of wire that is in the magnetic gap from the voice coil. And if you multiply those two values together, you get what we call the motor strength, or the BL. And that's how strongly the motor can push and pull the cone per unit of power. And if you go to a technical data sheet, you'll often find motor force, BL, listed there for you. And if you know the current at any particular time, and you know the speaker's BL, you can work out the actual force that's being applied to the cone at any particular point in time, which is super handy. But there's kind of one problem when it comes to data sheets. Not all manufacturers list all of this information. Often on the data sheets you will find B, such as the flux density, but you might not find the voice coil wire in gap value L. It might just list BL, but it might not list B and L separately. So in this case it does list B, but it doesn't list BL or L that I can see. I can't see the BL value. So what do you kind of do in these types of situations? How do you compare two different speakers if you haven't got all that information available? Well, one way to do it is to look for information relating to the voice coil itself. So in this case we have the voice coil diameter, the voice coil height, the number of layers or windings of the voice coil, and importantly the magnetic gap height. And I'll just show you what these things are. So some of them are pretty obvious. You have the voice coil wire length, so how much wire is used to make the voice coil. That's different to the amount of wire that's in the gap. The other one is voice coil diameter, so how it's a cylinder, so what's the diameter of that cylinder. And then there's the voice coil height, so how high is the stack of windings. And then of course the number of layers that we've talked about before, is it a single layer, a double layer, quad layer, that type of stuff, right? Because these are all parameters, characteristics that describe the voice coil. And then, if we have that information, and let's take this speaker here, we can take the voice coil diameter, which is 20 millimeters, the voice coil height, which is 7 millimeters, the voice coil gap, which is 3, and 2 layers, right? So the first thing we can figure out is just how much of the voice coil can be in the gap at any one time. And that's basically, the size of the gap, which is 3 mil, versus a 7 mil tall voice coil, right? Which means that 3 divided by 7 gives you 43%. That means 43% of the voice coil can actually be in the magnetic gap where it can be influenced strongly at any particular point in time. So that's an interesting measure to have. Then we can work out roughly the amount of wire that's available, in the gap, for want of a better term. And that's taking pi times the voice coil diameter, which is 20 mils, which means that we get 63 millimeters of wire. I have 2 layers. That's 126 millimeters of wire. Now, that's not an exact science because voice coils have different gauges of wire and that type of stuff, so it won't be 100% accurate, but it will give you a rough measurement that you can work with. So let's take a look at a second type of speaker. This one has a voice coil diameter of 38 millimeters, a height of 28, a gap height of 8, and it's a 4-layer voice coil, right? So let's run the numbers again. 8 millimeters divided, 8 millimeter gap by 28 millimeter voice coil means that only 28% of the voice coil can be in the gap at any one time. I've got 38 millimeter diameter. It's 119 millimeters per layer, or 477 millimeters of wire, because I've got 4 layers of voice coil wire, right? So I can lay these two sets of data next to each other. So in this one, I've got 43% of the voice coil is in the gap. This one's got 28. This one has 126 millimeters of wire. This has 477. So even though this has less of the voice coil in the gap, I've got more wire potentially in the gap than this one over here. Now, that's the way I would probably use the data, just to do some rough comparisons of different speakers, because the more voice coil that you have in the gap, the more wire that you have available, the stronger the motor is going to be. But it's not just a simple matter of going, oh look, I have a big voice coil, therefore it must be strong. No, it depends also on the gap height and how many layers of wire you've got. But to be fair, I'm not really comparing apples with apples here, because this is probably a mid-range voice coil, and this is probably a subwoofer voice coil, and that's why it's got so much more wire and such a big voice coil diameter, right, and height. But yeah, it's a way of also checking those things out. With all of this information, we can not only work out the speaker's BL, or motor strength, we can work out roughly how much of the voice coil is being acted upon, how much wire is roughly in the gap. But even with all of these things, there is, that's not the entire picture when it comes to motor strength. Okay, well, so far we've just been looking at the raw motor strength, how strongly the driver motor can push or pull the cone. But what we haven't considered is just how much mass the driver motor needs to move, and how much resistance from the speaker it needs to overcome. It's kind of like comparing two engines, but not really knowing whether they're in a big car or a small car, or whether those cars have to drive up steep mountain roads or not. So we're not really doing a full comparison where we're just looking at BL. So first of all, I'm going to look at the resistance part, and then we're going to come back to the mass. But on the resistance side, we talked about this formula a little earlier, that the amount of force that can be produced by a driver motor is the motor strength times the current. So because current is involved, it means that anything that affects the current or reduces the current flow through a voice coil will have an effect on the amount of motor force that the driver motor can produce. In other words, it's going to be acting as a resistant force against the motor. Now, we talked about things that affect current flow a little earlier. We touched on them, and one of those things was impedance. Now, we talked briefly about impedance, but I want to do a bit more of a deep dive, because it's an important topic in car audio that is a little tricky to get your head around. But most of you will be familiar with what we call nominal impedance, or Z-nom in shorthand, which is basically, whether you have a 2 ohm speaker or a 4 ohm speaker or an 8 ohm speaker, that type of thing. And it's really the class of impedance that your speaker has, right? It's your actual impedance is a lot more tricky to calculate, and it kind of looks a bit like this. It's made up of a whole bunch of things. But it's basically how hard it is for current to flow through a speaker, right? So a lot of people refer to this as the speaker's resistance. Like if we're talking about resistance in a length of wire or in an electrical circuit, that resistance is typically fixed, right? It doesn't change. And the reason that we talk about impedance with speakers instead of resistance is because impedance does change, right? It changes with the frequency, as we talked about a little earlier. But it gets a little complicated. I'm sorry, this looks like a super scary formula, but I promise it's not as scary as it looks. So impedance, or Z, is made up of a bunch of things, right? It's made up of electrical bits. So these are the electrical resistances that contribute to impedance or resistance. And then the bottom here is the mechanical bits, right? And so first of all, I just want to look at the electrical bits, and I will come back to the mechanical bits later. So impedance from an electrical point of view is made up of the voice coil resistance, the inductance of the voice coil, and the motor force squared, which equals a term called back EMF. But let me explain these terms again. So voice coil resistance is how resistant the voice coil is to current moving through it. Excuse me. It's not the same as impedance. It is kind of like a fixed value, right? It's to do with the thickness and the length of the wire that backs up the voice coil. So the more wire you have, the harder it is for current to flow through the voice coil, right? Whereas inductance, as we spoke about earlier, is about the voice coil's resistance to change in current direction, right? Like water flowing through a pipe and wanting to make that water flow in the opposite direction, right? The more often you do that, the quicker you do that, the stronger the resistance, right? And that's why inductance increases with frequency, because you're asking the current to change direction many more times a second than low frequencies, and we touched on that a little earlier. The third term is back electromotive force, or EMF. So this is basically the voice coil is moving up and down in a magnetic field, and it's a coil of wire, and that is exactly like a small generator. So while you have these magnetic forces pushing on the cone, you're actually generating a small amount of voltage as the voice coil goes up and down in the magnetic field. And anyway, that's essentially electromotive force, or back electromotive force. It's a voltage that works against the current in the voice coil, right? Or the voltage in the current in the voice coils. So all of these things add up to provide what we call an electro resistance to the force of the motor driver. Okay, so let's take a look at some of these a little closer. So voice coil resistance, as I said, is the amount of wire in the voice coil. The higher it is, the more resistant it is. And to be honest, this voice coil resistance is essentially what makes up how high ohms your speaker is, right? So if you've got a low voice coil resistance, you tend to be at 2 ohm speaker. If you've got a high voice coil resistance, you tend to be 8 or 16 ohm speaker. And when you look at how much of the impedance a voice coil makes up, so in a 4 ohm it's between 3 and 3.8 of the 4 ohms, it's 3/4 to nearly 90% of the speaker's nominal impedance is made up by the voice coil resistance, right? So that's kind of interesting. So the more resistant your voice coil, the more likely you are to have a higher ohm speaker. Now, why is that important? Because, as we said before, if you've got lower ohm speakers, it allows more current through, which means you can the amp can supply more power and the speaker can be louder, right? All things being equal. The second term is inductance. This is to do with, once again, the voice coil, how many loops of winding, how many layers of winding it has, and it's about resisting this change in direction of the current. A speaker with a high inductance, LE, will lose its top end sooner, and a speaker with a low LE will be more responsive at the top end. And that kind of makes sense because if this is about being resistant to sudden changes in direction for the current, something that has a high LE will resist that top end change more, right? And that's why you have more top end loss earlier than a low LE, right? Low LE, less resistance to that change. It's going to hold on in terms of the top end. Here are some of the LE measures, typical measures or ranges, mid-range 0.06 to 0.12. This is low, this would be high. Gives you a bit of an idea of, if you're looking at different speakers, how they kind of sit in terms of the typical ranges that you'll find for different speaker types. The third one is this back electromotive force. As I said, it's the back voltage that's being forced into the speaker by the voice coil acting like a mini generator, right? Now, it is strongest at what we call the speaker's resonant frequency, or FS, right? And I'm going to go into a lot of detail about FS a little bit later, but basically the reason for that is because the speaker is at its natural resonant frequency, so it wants to oscillate without a lot of energy being put into the system. And the EMF actually generates what we call a maximum impedance peak, which we'll take a look at a moment. So when you look at these different forces all acting on the motor force, you have the voice coil resistance, which applies a resistive force against the driver motor, which is the same all the time. You have an inductance force that is working against the motor, but that changes with frequency. And you have this back electromotive force that's working against the motor, but that gets stronger as you approach the speaker's FS value. So a moment ago I talked about the back EMF producing, a big, tall impedance spike, and here it is, right? Boom! That's the largely the voice coil acting like a generator, creating this back electromagnetic force, and you get this massive impedance spike because this is where that force is strongest. And why is it strongest at that point? Well, it's because the FS of a speaker is where the springiness of the suspension equals the inertia of the moving cone, right? It's a bit like being on a swing and having it swing back and forth and getting it just to the right point where you just sort of need to poke it to keep it moving, right? That's essentially what the FS is. And that means that the voice coil is bouncing up and down with its maximum excursion, right? And when it's doing that, and there's not a lot of force being applied electrically by the motor because the system wants to swing naturally, then you create a lot of back EMF force, electromagnetic force, and that's why you get a massive peak in the impedance, right? This impedance curve, right? There it is, and that's the way to tell where your speaker's FS is, right? Because the voice coil produces a big peak. While we're just looking at this impedance curve, just quickly, I talked about the inductance, going up with frequency, and you can see, we're curving up there, higher frequency to get more and more impedance, and that's because of the effect of inductance, right? Okay, just something a little interesting. The last note I'll make about this before we kind of move on is just the shape of the impedance curve. This impedance peak, I should say. If it's big and tall like this, it means that you have less dampening and less control around the resonant frequency. That means that the speaker is kind of a little more out of control. If it's a broad low peak, right, instead of going way up there, it just sort of like does this a little bit, that means that the speaker is more dampened and more in control. So you can kind of look at the shapes of these impedance curves and get a bit of a sense as to how a speaker might behave as it approaches the FS. All right, so now I'm going to talk about all of this stuff together. So we were able to work out some stuff about the motor force, excuse me, or the motor strength by looking at things like the voice coil diameter and the height and the magnetic gap height and the flux density and all of that stuff. And now we can add on some we can look at some data that relates to the electrical resistance that's applied to the motor that's working against it, which includes the nominal resistance of your speaker, what class it's in, the resistance of the voice coil, which is RE, the voice coil inductance. In this case, it's shorthand LBM, but it's usually LE. So you can look at those types of things and get a bit of a sense of how much force is being applied against the motor. But then there are the mechanical parts. When we looked at that formula earlier, that includes the moving mass and the mechanical resistance, right? These two values down here. Now, I'm not going to go into a lot of those details. I'm going to talk about that stuff a little bit later in the tutorial. But the moving mass is basically all the parts of the speaker that moves, the cone, the voice coil, the suspension, all of that stuff. And that's MMS. And then the mechanical resistance is how much energy is lost as all that moving mass sort of flaps around, right? Now, all of those things are working against the motor has to move a certain amount of mass, and the motor has to overcome a certain amount of mechanical resistance. So between all of this stuff and all of this stuff and these things, you can get a lot of information about the motor strength of a driver motor and the things and the forces that are working against it, right? Yeah, so that's all a bit complicated, right? I mean, that's pretty technical. I'm even giving myself a headache just talking about that stuff. There must be quicker ways of just comparing speaker motor drivers, right? And yeah, there are some shortcuts, right? And one of them we already talked about is the just using BL, right? Looking at the magnetic flux density in the gap and multiplying it by the VC wire in the gap, or just reading it straight off the technical data sheets. The only problem with that is that it ignores any electrical and mechanical resistance and any moving mass, right? It's just looking at the raw strength of the motor. To get a better idea of, we can use a formula called take the motor strength and square it, and then divide it by the voice coil resistance, right? So what this does is it takes into account the main electrical resistance, but it ignores the mechanical resistance. If you want a formula that includes the mechanical resistance as well, then you can have BL squared divided by voice coil resistance times moving mass, right? And that, if you use that little formula, if you grab the BL value off the tech data sheet, you grab the voice coil resistance of the data sheet and the moving mass, plug that all into the formula, it'll give you a number, and then you can compare two speakers of the same class and have probably the most accurate measure or comparison of its motor strength. And that way you're not relying on looking at magnet size or voice coil size or whether I'm using a neo magnet or not. Something as simple as that will take all of the major factors into account and give you a really good apple-to-apple comparison for two speakers. So that is how to determine driver motor strength. So the speaker cone is made up of the cone, the dust cap, and the surround. The cone is attached to the voice coil, so as the voice coil moves back and forth, it pushes and pulls the cone, and it's the cone that actually creates the pressure waves that we hear as sound. The surround we touched on earlier is the outer rim of the cone that connects the cone to the basket and provides that flex, or allows the cone to move up and down and flex. And the surround, as we spoke earlier, is part of the speaker suspension. And then of course there's the dust cap that's there to stop, dirt and rocks and foreign objects and things getting into the driver motor and into the magnetic gap. Now often you'll find the dust cap looks like the top of a bullet, or is shaped in a crazy weird way, and it has a role to play with acting like a waveguide for the sound waves. But yeah, that's a completely different topic. So, talking about the parameters that apply to the cone, or the speaker cone, the first one is cone area, which has the shorthand SD. Now, there are, all familiar with 6.5-inch speakers and 3.5-inch speakers and 12-inch speakers and all that stuff, but not all 6.5-inch speakers have the same cone area. So if you want to compare two 6.5-inch speakers and find out which one has the bigger cone area, then this is the parameter to look for, SD. Now, closely related to that is a parameter called displacement capacity, which is VD. So that is the amount, or the maximum volume of air that a speaker can move with each forward or backwards stroke. The way you work that out is you take the cone area of the speaker and you multiply it by the Xmax of the speaker. Now, we'll talk a lot more about Xmax later, but it's basically how far the speaker can move either forward or back without distorting. So you can think about it like the maximum stroke of a speaker. So why is this an important spec? And the answer to that is because a higher VD value, or displacement capacity value, the deeper the bass, the more volume it will make. And this is especially important when you're comparing subwoofers or mid-bass speakers. All right, so when you have a look at a data sheet, a technical data sheet, you'll find something like this. So here is the cone area of this speaker at 202 centimeters. So this is, I think this is an 8-inch from memory. So if you want to compare to 8-inch, for example, you could have a look at their cone area and find out which one's got the bigger cone area, because bigger cone areas generally mean more loudness. Now, if you want to then work out the displacement capacity, often you'll find that's not listed on the specification sheet, but it's pretty easy to calculate. And so here's an example. Here's the cone area. Here is the Xmax of the speaker, how far it can move in one direction. And we just simply multiply the two together. So in this case, 202 centimeters by 10 millimeters. Now, before you multiply, you have to put everything into the same units. So 10 millimeters is 1 centimeter. So now we have everything in centimeters. I can now multiply them together. So 202 by 1 is 202 cubic centimeters, which is 200 milliliters, or 0.2 of a liter. Now that is the maximum, or the Xmax from center point to forward. So if you want to work out what the total peak to peak air movement of a speaker is, then of course you double this. So peak to peak would be 0.4 of a litre, right? And as I said, this is handy if you wanted to have a look at two subwoofers and find out which one is more likely to make more bass, just by comparing the displacement capacities. All right, the next set of specifications is around mass. So the first one is what we call total moving mass, MMS. Now we talked about, or touched on this earlier when we were talking about driver strength, or sorry, the driver motor strength, because the driver motor of the speaker has to move the moving, the moving mass back and forward, right? If you think about it, some parts of the speaker move, some part of the speakers don't. All the parts of the speaker that moves are included in the total moving mass calculation. So for example, the things that move are the voice coil, the cone, the surround, the dust cap, the spider, the flexible spider part, so the suspension parts of the speaker. But what doesn't move is the basket, the magnet, the top plate, the bottom plate. Those things are static, they're fixed. So we're looking at the weight or the mass that the motor has to move back and forward. Now, this also includes the air, because we don't run our speakers in a vacuum, and air has a certain amount of mass. So, for example, if the motor has to push the speaker, it also has to push the speaker and the air in front of it, and when it pulls the speaker back, it has to do the same thing. There'll be air around the suspension and the spider, and air around the cone, and all that has mass. So why is this figure very important? Well, because the higher the total moving mass, the bigger the motor that you need to be able to accelerate it and brake it, and and control the cone's movement, right? So, for example, if you have a speaker with a high moving mass, but it has a very small BL value or motor force value, then that speaker is more likely to be more difficult to control and have less sound quality, because the motor won't be able to control it as well, right? I'm generalizing, but yeah, that's the main idea. So if you're comparing two speakers and you look at the moving mass and you look at the motor force, you can get a bit of an idea which one's going to be more controlled than the other. Now, there's a related parameter which is called the mechanical moving mass, which is MMD. Now, this is just the mass of the mechanical parts. It excludes the air, right? So total moving mass is MMD plus air, right? So if you want to find out how much air is related to the in the moving mass, then find the MMD value and subtract it from that, and that will tell you how much air is making up of the system's MMS. Now, once again, you could find, it's usually difficult to find the MMD. Some manufacturers list it. In this case, we're looking at this little 8-inch subwoofer, and it has a moving mass of 95 grams. All right, so that is speaker cones. Okay, next we're going to take a look at the speaker suspension, and the suspension is made up of the surround and the spider, and together they act like the shock absorbers in a car or the springs on the trampoline. They allow the cone and the voice coil to move freely back and forward, while making sure it stays centered and aligned with the magnetic gap, right? So the suspension, along with the drive motor, controls how the speaker responds, especially around the resonant frequency. But we'll talk about the resonant frequency a little bit later. When we talk about suspension, we use the term suspension mechanical compliance, or shorthand is CMS. Now, compliance, it's a bit of a weird way of thinking about, because often when you think about suspension, you naturally think about, oh, well, how stiff is the speaker? But the word compliance means how compliant the suspension is, or how compliant the speaker is. How much or how easily does it give or move when force is applied. So speakers with a high CMF are not stiff. That means that they are highly compliant or easier to move, so they're softer, right? A lower CMS doesn't mean that it's softer. It means that it is less compliant, it is stiffer and harder to move. So it feels a bit weird talking about it that way. To me, it feels kind of backwards, but that's the way it kind of is. But there just happens to be a term for stiffness. That's called the suspension mechanical stiffness parameter, and that has the shorthand KMS. It's basically the inverse of CMS. A high KMS means it's stiff, a low KMS means it's soft. But you generally don't find KMS on the technical data sheets. You tend to find CMS. Okay, well, this is the formula for CMS. It's related to the resonant frequency and the moving mass of a speaker, and we'll come back to resonant frequency and how CMS and moving mass are related to it later. But what I want to do is explain how this speaker compliance stiffness thing kind of works. So here I have a diagram of a speaker in 3 different states. or stages of its oscillation, right? And here in green is the motor, here in blue is this voice coil and the cone, in red is the surround and the spider, which is the suspension. And when nothing's happening, the suspension holds the cone in what we call its resting position, right? And so if you've got a speaker in the cupboard and you push on it, it'll bounce up and down. But just sitting there, it'll just sit in kind of this midway point where everything's in equilibrium, right? The spring's not pulling on the cone or doing anything, it's just kind of sitting there, right? And this is the resting position of a speaker. Now, when we push the speaker forward, so the motor drives the voice coil forward, which pushes the cone forward, it will stretch the suspension of the speaker, right? Stretch it out like a spring. It'll get to a point where the spring goes, okay, that's enough, and starts pulling the cone back towards its resting point, right? It naturally wants to pull because it's like a stretched spring, right? And then, of course, you'll pull the speaker back to its resting position, and of course it'll go past that point because the drive motor is pulling the voice coil down now, and once again the springs are being stretched but in the opposite direction, right? So there's this natural kind of competing or oscillating spring force that is being pulled in, back and forward and back and forward and back and forward, right? And so yeah, the stiffness of the suspension will kind of affect how the speaker behaves. Because if you think about it, let's say we have really stiff springs, right? What that means is that it's going to be harder for the motor driver to push the cone. The springs are going to be pulling very hard on the cones. That means it won't extend, or the excursion of the cone will be less. And when the spring starts pulling on the cone, it's going to pull this back very quickly, right? Back to the resting position very quickly. So a stiff spring means that the cone is much tighter control over the cone. The cone, is going to stay nice and centered within the magnetic gap. And, it's not going to extend as far, right? Because you've got this very high spring force, working on the cone as it moves up and down. Now compare that to a soft spring, right? This is a soft spring now, and so these forces are much weaker, which means that it's easier to push the cone. The cone can extend further because the spring is a weaker spring, so you can push it further. When the spring pulls it back to its resting position, that's going to happen slower because the spring forces are less. But what that also means for the speaker is that the cone is less controlled, right? It takes less energy to move the cone back and forward. But so that's why the stiffness of the suspension is important, because it tells us how controlled and how the speaker will behave. So this is especially important when we're looking at mid-bass and subs. So if you think about a sub with a very stiff suspension, okay, it's going to be harder to move. You need more power, to get over the high spring forces, but the cone's going to stay in control. There's less chance of it going beyond its Xmax and getting out of become overextended. And you tend to find that the bass is going to be much tighter and punchier, right, with a sub with a stiff suspension, right? And those types of subs work really well in ported or sealed boxes. And it's why the SPL guys love stiff suspension subwoofers, because you can throw more power at them. The sub will stay more controlled, more centered centered on the in the magnetic gap, so they'll take more power, right? More power means more loudness, and that's why they like them. Compared to a soft suspension subwoofer, the cone's going to be easy to move. You need less power. You need a smaller motor. So sometimes, but because there's less control, the bass can become a little loose and boomy, because the cone can overhang, but it's also much easier to get deeper bass, right? Because the cone extends more, and it's slower to return, so you get longer wavelengths, right? Yeah, so these types of subwoofers are better suited to free air and infinite baffle. But you do need to make sure that if you've got a soft suspension sub and you're using it for sound quality, that you need a good strong motor and good dampening or a high QTS to compensate for the lack of control of the cone by the speaker suspension, right? Okay, so when we look at the CMS values for different speakers, or I'm just going to pick 6.5 mid bass and 12-inch subs just as a category. Let's say you're going to pick a 6.5-inch mid bass, and I'm going to put that in the doors in an enclosure, right? A custom box. Then you really want to look at a CMS of less than 0.3 because you want a stiff mid bass in an enclosure, right? If you're going to put the mid bass in the doors in the rings and vent it into the door void, then you want a pretty soft mid bass, something with a CMS greater than 0.5. And the same applies for your subs. If you're going to put the sub in a box, you want and you're looking for SPL, then you probably want something that's less than 0.13. If you're going more for, I guess, SQ and deeper bass, then you kind of want a sub that is in free air, and you're looking at a CMS of 0.2 or greater. But these are just guides, just examples, right? So what I want to talk about next is what happens when you put a speaker in a box. And I guess the first thing to sort of explain is when you have air in a enclosed area, the air acts like a spring because you're trying to compress it, right? And it works against the forces of compression, right? Now, if you're in free air, however, like this, there is no air spring, right? There's no pressure going on. It only really works when you're in a box of a certain size. So if the box is too big, you have very weak air spring. If the box is small, then you'll have a very strong air spring, right? Yeah, and if you think about the SPL guys again, the guys are aiming for big dB, 130, 140 dB and more. Putting a stiff spring speaker into a box is fabulous because you not only get the control of the cone from the stiffer suspension, but you now get added suspension because of this extra air spring, right? So in a box you get both the mechanical suspension forces and the air spring forces working on the cone, right? And it becomes stiffer, even more power can be thrown at it, and I can get even louder decibels out of it, right? If that kind of makes sense. So this air spring has a proper term or proper technical term. It's called the acoustic compliance in a box, and the shorthand for that is CAB, C-A-B, right? Now, you'll often see the word acoustic used by technical engineering geek guys. It just basically means air, right? So you can interchange acoustic and air. So the air spring or the acoustic suspension are the same kind of thing. And of course, we know that compliance in the term, we know what compliance means. It's how easy it is to move when force is applied. And the thing about the air spring or the acoustic suspension is it is dependent on box size, right? So if you have a big box, there's much less air spring. If you have a small box, you have a high air spring, right? And that's important because it will affect the suspension of the speaker and therefore the level of control, and of course how the speaker will behave. Now, while we're talking about air springs and things like that, a term you might have heard of before is VAS, V-A-S, and that is what we call the equivalent compliance volume. It's the volume of air. So if you had air trapped in a box, it'll have that air, when you press on it, will have the same springiness as the speaker suspension in free air, right? So it is basically CMS, or the suspension springiness, expressed as air suspension, right? Now, VAS is not the size of a box you need for your speaker, right? It is just what we call the equivalent air spring to the speaker's mechanical suspension, right? And that's important because we use this VAS to calculate the ideal box size for your speaker, right? And later in the tutorial, I'm going to take you through how to use VAS to do exactly that. So just to reinforce that point, when you go to your technical sheet and you look this up and it says, 58 litres or whatever this thing is down here, that does not mean you need a 58 litre box. It's just the 58 litres of air will be equivalent to this this CMS value here, right? So we use that in doing calculations. It's not the box size that you actually need. Right, just to wrap up the whole speaker suspension piece, I just want to talk about mechanical resistance. Now, mechanical resistance is part of the speaker dampening and combines with electrical resistance. We'll talk about dampening once again later in the tutorial. But essentially, mechanical resistance, or RMS is the shorthand, is the amount of energy that's lost due to the resistance that the suspension has to flexing, friction that's going on in the spider, the air it needs to sort of drag back and forth, air in the magnetic gap and around the cone, things like that. All of these things have a dampening effect and work against the force of the motor, right? So if you think about it, if our spider and surround was infinitely flexible, right, and things moved without any friction, then you wouldn't have any mechanical resistance. But in the real world, surrounds and spiders require a certain amount of force to get them to flex, and there's a certain amount of friction depending on your speaker design, and this is measured in mechanical resistance. And so you can find this once again on your data sheets. It's the term RMS, and you don't tend to really look at RMS when you're thinking about speaker suspension. It's more used when you're looking at the dampening factor of a speaker. So dampening is how quickly, if something's bouncing up and down, how quickly it stops bouncing up and down, right? But as I said, we'll come back to dampening a little later in the tutorial. So yeah, that's all about speaker suspension. Okay, well, so far we've covered a fair bit of ground, and we've been looking at the speaker specifications or parameters relating to different components of the speaker. So, the motor, we looked at things like the voice coil dimensions, the height, the layers, the magnetic gap, and how much voice coil is in the magnetic gap, and flux densities, and all of that type of thing. We then looked at the cone, about its area, its displacement, what the moving mass was, and then of course the suspension, its compliance, its stiffness, its mechanical resistance, what the air sprig and what VAS meant. So we've covered a fair bit of ground, and when you're looking at a technical specification for a speaker, we've looked at probably half the terms that you would find there. These things like impedance and DC resistance of the voice coil, things like the moving mass, the suspension compliance, the equivalent air spring volume. What's this one here? SD is the cone area. BL is the motor force of the motor driver. So we've gone through a fair bit of stuff, but there's still a lot to look at. We have the wattage of the speaker, and how much power it can handle, the sensitivity of the speaker, things to do with QTS and dampening, sound pressure levels, Xmax, resonant frequencies, a whole bunch of stuff, right? But these are all terms that relate to how the speaker works together as a whole, as opposed to separate components. So we're going to move on to look at those parameters next, starting with Excursion. Okay, so we're going to start by talking about excursion. Now, excursion is how far a speaker cone can move back and forward. Um, it's measured in generally from one direction, so from the speaker's resting position to fully extended forward or fully extended back. And it's usually measured in millimeters or inches. Now, there are two terms to describe excursion. One is called Xmax and one is called Xmech. And you've probably heard of Xmax before. It's a very common parameter in car audio, but it's largely misunderstood. So what is Xmax? Well, Xmax is the maximum distance that a speaker can move in and out but still remain linear and controlled and play without distortion. Now, the reason Xmax is so interesting is because Xmax is related to how much air the speaker can move. If you remember when we talked about cone, Xmax times the area of the cone equals the displacement volume of the speaker. So that means the bigger Xmax, the louder you can generally play, right? And that's why Xmax is such a popular parameter when you're looking at speaker specifications. So Xmax is how far the speaker can move and stay undistorted. Xmex is the actual physical limit of the cone's travel, right? So it's how physically far it can travel forward and back before the speaker gets damaged, right? So when we look at technical data sheets, we tend to find Xmax is generally on the sheets, but Xmex is not. So in this case, this speaker has an Xmax of 10 millimeters or 3/8 of an inch. And if you want to calculate out what the Xmax actually is, you just take the voice coil height and the gap height from each other and then divide it by 2. We talked about the voice coil height and gap height when we were looking at the driver motor. So you can read those things off the technical data sheet, and then you can kind of do the math. So we've got a voice coil height of 28. We've got a magnetic gap height of 8. We subtract one for the other, divide it by 2, and we end up with an Xmax of 10 millimeters, right? So, here it is. So the big question is, I want a speaker with big Xmax to make lots of loudness, but can I play my speakers above Xmax? And the short answer is, well, yes, but let me explain. So below Xmax, your speaker is cruising along. It's playing as the speaker was designed to play, right? Everything is behaving itself. The speaker cone is moving up and down like a piston. The electrical and the magnetic forces are within the design parameters, and so the speaker is just playing the way it should, a bit like driving your car and, cruising along. And, the audio signal is being accurately and cleanly replicated by the speaker, and there's no distortion. So, happy days. It's exactly the way the speaker was designed to operate, right? But once you go above the Xmax, the speaker is no longer moving in a linear and controlled fashion, right? It starts to sort of get the speed wobbles. It's a bit like driving your car above red line, right? You can drive it there, but the motor really doesn't like it, okay? So what happens is if you push your speaker above Xmax, you start to get distortion. The more you push it, the worse the sound quality gets. Gets muddy, blurry, because you're pushing the speaker above its design limits, right? The cone starts to flex and distort. The suspension is less controlled. The voice coil moving up and down in the gap is no longer as linear as it was. You get much stronger back EMP strengths, and changes in the way the magnetic field behaves. So you really are pushing the speaker beyond its design limits. It can still play there, but you suffer in terms of distortion and sound quality. And then, if you push it above the Xmech, which is the physical limit, well, okay, now you're going to potentially cause damage to the speaker. The voice coil could bottom out and hit the bottom of the magnetic gap. Because the speaker cone is now so uncontrolled, you can have the voice coil striking the pole piece or the top plate or something like that, or getting jammed in the magnetic gap. The cone could tear, the spider could tear, the tinsel leads could tear, a whole bunch of things. So you'll hear knocking, hammering, buzzing, or the speaker will just suddenly stop driving. So it's very much like driving your car beyond your red line limits, and eventually the engine's going to fail. So another way of thinking about it is, I'm driving my car along, revs 2,000 or 3,000 revs, everything's nice, I'm operating within the speaker's design parameter and everything is working super well together. I keep turning up the volume, everything's still clean and sounds great, but as you approach the Xmax limit and you go over that point, then the speaker starts to distort, things start to sound less clear, the bass gets less muddy. So it doesn't suddenly go from clean to distorted, it's a gradual worsening of the sound quality, right? So you can push it into the Xmax, but it's, as I said, it's like driving your car in the red line zone, right? And then if you really start pushing it well into the Xmax area and beyond and into the Xmax area, then you're in the danger zone, and that's when speakers suddenly fail. So next we're going to move on and take a look at FS, or resonant frequency. Now, you might have heard of the term free air resonant frequency, often shortened to resonant frequency or just plain old FS. Now, it's a term that a lot of people have heard of, but many people don't really understand exactly what it means. Now, we use the FS to work out what size of box that we might want to use, or we look up the FS on a subwoofer data sheet to figure out how low that sub might play, and we use the FS to choose crossovers to make sure that our speakers are protected from low frequency excursions such as tweeters and mid-ranges. But when you look at a data sheet, you are looking for the term resonant frequency or FS. It's commonly listed on data sheets, and it will be a specific frequency for that speaker. And in this case, this speaker has a FS of 54.5 Hertz. Now, a lot of people think that FS is the lowest frequency that you can play your speaker, and well, that's not entirely true. It's a little bit like Xmax. People kind of have the wrong idea about this, but I'll explain what FS is and whether you can play lower than that later in this part of the tutorial. But first of all, FS is calculated using this formula. It is not a fixed value. It's a fixed value, but it's unique to your speaker based on your speaker's moving mass and suspension compliance. And in fact, you can change the FS frequency by putting the speaker in a ported or sealed box. But once again, we'll come to that a little bit later. So now, if this formula looks a little bit familiar, we actually touched upon it when we were looking at the speaker suspension and working out how to calculate the CMS. It's the same formula, just kind of rearranged. So to understand FS, we need to understand a term called resonance. And to understand resonance, I need to share a couple of terms with you and explain what they look like when we're talking about speakers. So mass is an easy one. It's basically how heavy something is. And when we're talking about a speaker, we're talking about the speaker's moving mass and how heavy that moving mass is. So some speakers have a lot of cone area, big voice coils, heavy suspension, and so they'll have a heavy moving mass. other speakers, clearly smaller, lightweight materials, will have a lighter moving mass. The second term related to it is inertia. So how hard is something to get started moving? How hard is it to stop it once it gets moving? So think about a soccer ball, right? That's pretty easy to get rolling along. You just give it a little kick and off she goes. Compared to pushing a car, right? For example, I mean they use two different lots of energy, right? So that is inertia. It's related to how hard something is to get accelerating and to brake it once it's starting to move. So once again, when we think about our speakers, we're really talking about the inertia in the moving mass. So when the cone's moving this way, first of all, it takes the speaker motor to get the cone moving. So the inertia in accelerating that speaker cone and getting it moving, and then changing the cone's direction. Now, if it's a very heavy moving mass, then you need more force from the motor to get it started and to change the direction of the cone, compared to something that has a lighter moving mass, will have less inertia. Now, the next term is ringing and damping. So ringing is how much a object wants to oscillate or vibrate, and good examples of that are a guitar, string, a bell, things like that, versus, for example, a house brick, right? House bricks don't want to ring very much. Now, dampening is once an object is ringing, how quickly those oscillations or vibrations stop. A good example is shock absorbers in your car. They bounce up and down a couple of times, but without those shock absorbers, you'd have, the car would bounce a lot more. So that is the term damping. Now, we use damping when we're doing sound treatment in a car. So, for example, putting butyl sheets on the door skin, inside the car door to, stop the panels resonating and vibrating, right? So that's damping. And in a speaker, damping is basically controlled by the suspension and the dampening electronic and mechanical dampening forces, which relate to a term called Q. Now, to explain damping, I want to take you back to a slide that we looked at earlier when we were talking about the speaker suspension. When the speaker is at its resting position, there's no force on the springs and the cone's not moving, so there's no oscillation. When the cone is moving forward, then the speaker is going that way, it's stretching the suspension, and of course we get a spring force that is working in the opposite direction to the way that the cone is moving, and eventually it gets to its maximum excursion, and the spring and the motor pull it back. And then it passes the midpoint and then sort of reaches its bottom of the oscillation, right, where the spring is stretched again. And so we get this, this back and forward oscillation, right? We talked about that in detail before. Now, one thing we didn't talk about was another force called damping. So damping is a force that resists the cone movement, right? So it works against the driver motor. And so there are two types of damping. There is electrical damping, which is made up of basically the back electromagnetic force, where the voice coil, as a coil of wire, is moving through a magnetic field, so it then acts like a mini generator and creating a voltage which is an opposing force to the driver motor. And then the second type of damping force is the mechanical damping. Now, we talked about this earlier when we were talking about the suspension, and that is the mechanical or the energy losses due to friction and flexing of the cone and the spider and all of that, and air that's dragging around with it. And that's mechanical damping, right? So there's these two damping forces. Now, in car audio, when we talk about damping in a speaker, we talk about the quality or the Q measure, right? And which is a bit strange, but why do we talk about quality when we talk about damping? And it's because it comes from the golden age of bell making, right? When back in the day, a good bell would ring for a long time. So, if you were a good bell maker, your bells would ring for ages, and, they would be said to have a high Q or high quality bells, right? They were not very well dampened, so, they'd ring for ages. But, if you were you know, a lesser bell making god and your your bells didn't ring quite as well, then you were said to have lower quality bells, right, or a lower Q, because they were more dampened and didn't resonate or vibrate or oscillate for as long, right? But in car audio, we don't necessarily want our speakers to be incredibly ringy, because what that means is, we'll get notes overhanging, and the sound will be boomy or a lot muddier. So we don't want no ringing, but we don't want over ringing either. So we want a certain amount of damping, but not excessive or not enough. So the term that you guys are probably familiar with or have heard before is a term called QTS, which is the total quality in free air. So when we talk about quality, we're talking about how well the bell rings, or in this case the speaker oscillates, how dampened it is. So if you have a low QTS where the speaker is well dampened, you'll have a small number like 0.35 or 0.4 or something like that. And these, it's a bit like having a stiff suspension. These are better suited for speakers in sealed or ported boxes, right? And often we'll use QTS for exactly this this purpose, is to find out what type of enclosure the speaker is probably best suited for, right? And if you have a speaker that is not well dampened and it has a high QTS value, like 0.6, 0.7, whatever, then it's better suited to free air and IB applications, right? And yeah, so that's traditionally what we've used QTS for when we're doing car audio. Now, QTS is actually made up of the two types of dampening forces, the electrical dampening and the mechanical dampening, and we call that the electrical Q of a driver and the mechanical Q of a driver, and of course the S stands for free air. So when we're looking on the technical data sheets, nearly all of them will list the QTS, so you'll know what the total dampening factor is. And sometimes they will also list the electrical and the mechanical dampening factors. Now, you would think that QTS would simply be the electrical plus the mechanical. It doesn't quite work that way. Here is the formula for working it out if you're interested in that kind of thing. Alright, so now we can go back to our original diagram and start putting some labels on it. So the electrical dampening is QES, the mechanical dampening is QMS, and the combined dampening is the total dampening force, right? Fabulous. So let's go back and have a look at our diagrams, because what has this all got to do with FS? If we just get rid of damping and the motor force, we'll come back to those things a little bit later. But just to explain FS, or the resonant frequency, we need to look at inertia versus the spring restorative forces, right? And I'm just going to call that spring force for a better term, right? So, as we said before, when the spring is, when the cone is fully extended, then we have this spring force trying to drag the cone back along with the motor force, but we're not going to talk about motor force for a minute. We're just talking spring versus inertia. And when it's at the bottom of its oscillation, we have the spring wanting to drag the pull the cone up, against the inertia, right? And so we have this oscillation, or this tug of war between the inertia of the mass of the cone movement and the spring strength of the suspension. Up, down, up, down, up, down, right? Now, when something is moving quickly, it has more inertia, right? So if you think about a car, which is stationary and you're trying to push it, okay, it's hard to push, but it doesn't move very fast. But if you have a car traveling at 60 miles an hour, that's got a lot of inertia, right? It's if it's going to hit something, it's going to do a lot of damage. So the faster something's moving, the more inertia it has, the harder it is to slow down, the more energy it takes. So when a cone is moving quickly, right, it has more inertia, and so at high frequencies, when it's moving back and forth very quickly, the inertia of the cone, or those forces, outweigh the spring forces. And of course, the motor, the drive motor of the speaker, has to play a much bigger role in controlling the cone, right? Because the inertia is dominating the forces that are involved in this oscillation. But it's quite the opposite at low frequencies. At low frequencies, the cone is moving very slowly, so it's easier to control in terms of back and forth movement. And then the spring forces outweigh the inertia forces, right? And of course, then the motor is working against the spring forces more than it is against the cone, right? And that's quite difficult to control the cone because it's actually trying to control the spring, not the cone movement, right? So for best speaker control, we actually want the motor to be controlling. Sorry, we want the motor to be controlling the speaker via its inertia, right? And the spring just providing, that extra bit of support. At low frequencies, that's the opposite to what we really want for good cone control. And so remember that, because that's going to be important when we look at the FS value. So, okay, so if we have inertia outweighing springs at high frequencies and springs outweighing inertia at low frequencies, what is the FS? Well, glad you asked. The FS is the point where these forces balance out. So the spring force and the inertia force is at the same level, and that happens at one specific frequency, and we call that the resonant frequency. The reason we call it the resonant frequency is because the speaker wants to resonate, right? It's at the position where it's at its easiest for the cone to move up and down and oscillate, right? It's a little bit like having a swing that is sort of moving along, and it's just at the right pace, so that you just need to give it a tiny little push and it will keep going. And it's the same when a speaker is at its resonant frequency. You don't need very much power from the driver motor to keep the cone in movement, because it's at its resonant frequency and it wants to oscillate naturally, right? So that's what the FS is. It's when these two forces are in balance. And so when you look at some of these impedance charts, this is the FS, right? This peak that you get in the impedance chart. Now, I'm not an electrical engineer, so I might not have this absolutely right, but my understanding is impedance is the resistance, or the speaker's resistance to current, right? So we know that as you go up in frequency, the inductance causes the impedance to rise, because inductance rises with frequency, right? So you see that there. But this big peak here, I think, is being caused by the back EMF, right? That electrical damping that occurs, because the cone is moving at its sort of greatest excursion. Therefore, the voice coil is moving to the magnet with its greatest pitch, for want of a better term. That's probably not the right term, but it's creating the biggest electric back EMF force, right? And so you get this big peak in the impedance curve. I think that's how it works. Please correct me if somebody who is an electrical engineer might be able to tell me whether I'm on the right track there or not. But it's something like that. That's why there's a big peak in the impedance curve. But this is the resonant frequency, where the speaker is moving very easily with very little force from the motor, because it's at that natural point where the suspension and the inertia is balanced out. So what's going on above and below the resonant frequency? Well, above the resonant frequency, the cone is moving a lot faster, and therefore it's being controlled more by the inertia, or the moving mass, and the driver needs to use more force to accelerate and brake that moving mass, right? So that's what's happening above the FS. When you get to the FS, those forces are balanced out and it naturally wants to oscillate. And then below the FS, we're getting down into low frequencies now. The the cone is being controlled by the suspension or the spring forces, right, the CMS, and the and then the motor driver needs to work against the suspension to compress and extend the compression, and it's not being helped by the inertia of the moving mass, right? So it's having to do a lot more work to push and pull that spring instead of pushing and pulling the cone, right? If that makes sense. And as I said, here at the FS, that inertia and spring cancel each other out, right? And at this point, how the cone is behaving is now being controlled by the amount of damping that the speaker has, or its QTS value, right? So let's have a look at how that kind of works, right? So when we have damping involved in this, right, so we're at the resonant frequency, these forces are balancing out, and now the only thing that's really stopping this speaker from not continuing to oscillate, or how long it oscillates for, is the level of damping. So if we have a low damping, a high QTC, it's not going to, this is going to oscillate longer because we have weak mechanical damping, we have weak electrical damping, and this is, this natural oscillation that wants to occur is going to keep going on. So at the resonant frequency, it's going to ring. Whereas if we have high damping, low QTC, it means that we have strong suspension losses and strong back EMF, which means that we have some forces working to slow the cone down, right? So at the FS, this is going to not oscillate as long, right, when we have high damping. So this is why damping is important, because it controls the behavior of the speaker at the resonant frequency or around the resonant frequency. And the way that that plays out when you look at the impedance curve is it affects the shape. So with a high QTS, low damping, things are going to bounce around and be uncontrolled and all that stuff. So we end up with a bigger peak, taller response, more ringing and vibration, less cone control. And this typically, if it's a subwoofer, will get boomier bass, right? Because the bass is not pulling up nice and clean. The notes are overhanging, right? And with high damping, low QTS, we end up with a smaller peak, right? It's flatter and smaller, or wider and smaller, because we're getting less oscillations. There's more cone control because the damping is high and it's controlling the cone from from excursioning and stuff. And what we end up with is a much tighter bass, right? Because the cone is more controlled at the FS, right? So you can tell a lot just by looking at the impedance curves, what's going on. So for example, let's look at a couple of 6.5-inch mid bass. Here's speaker A. And we can see here's the impedance curve, tall and high. We have an FS of 70, 14 grams of moving mass, suspension of 3.6, and a QTS of 7.9, which is pretty high, right? So that's very soft suspension. Okay, so let's have a look at speaker B. Okay, so this example, it has a higher moving mass, right, and a slightly stiffer, softer suspension. So that means that the FS value will be lower, but the dampening level is higher, so that means the curve will be wider and shorter. And that's exactly what we see here in this technical sheet. So while you can look at any of these numbers by themselves, you really need to kind of look at them in combination to understand how a particular speaker will perform. So in this case, speaker 1's going to be a little boomier in terms of mid bass because very soft, soft suspension and low dampening. So it's going to resonate and ring, and then this one has stiffer suspension, more dampening, and you can see that in the impedance peak, right? The shape of the impedance peak. So this brings us back to the question of, can I play my speakers below the FS? Well, it's a little bit like the Xmax Xmech situation that we spoke about earlier. So, before we said, this side of the FS, the speaker is dominated by the cone inertia. This side of the FS, the speaker control is dominated by the spring forces, and the speaker driver wants to control the cone. It's not so good controlling the cone by controlling the spring forces, right? So it's going to play better, and it's designed to play on this side of the FS. So we would call this the safe zone, right? This is where you'll have clean playback, low distortion. The excursion of the cone is within its operating parameters, right, within Xmax. But as you approach the FS, a bit like going over the Xmax value, things start to get less controlled, things start to get more distorted. Often you will find that you're getting over your Xmax, and I'll talk about that a little bit later, but it's to do with low frequencies require more excursion. So as you go down, you need more and more excursion from the speaker. You can play into your FS, but you're in the high risk zone. And then when you get below the FS, now you're asking the speaker to do more. You need more excursion to maintain the same SP level. It's about 4 times the excursion of SP. So if you're doing 2 mils of excursion over here, to get the same output level for a frequency down here, then you're now going to have to do 8 millimeters of excursion, and that might exceed your Xmax. So higher distortion, more power. You're really into the zone of potentially over-excursion on your speakers, and potentially heat and mechanical damage, right? Because you need more power to get the same SPL level. So the short answer is, can you play down to your FS or beyond your FS? And the short answer is it depends on the speakers that you're talking about. So when you sort of look at tweeters, mids, mid-bass, and subs, you want to kind of play in the safe zone. How far from the FS value, can you get, or how close to the FS value can you play safely? Well, for tweeters, they don't have very little excursion, right? Because they're designed to play very high frequencies, lots of oscillations per second. So they're going to have tiny, tiny, tiny excursions. So they still have an FS. They still have a value where the restorative forces and the inertia of the cone balance out. But you don't want the speaker playing at that level, because that'll be its maximum excursion level. So for a tweeter, you want to be 2 to 2.5 times from its FS. That's if you're using 24 dB slopes. So for example, if you have a tweeter with an FS of 1500, that would mean that 2 times would be 3000. Another half would be, call it 750. So at least 3750 hertz would be your absolute minimum for to put a safe crossover in for that tweeter. If you're using more gentle slopes, then you want to increase that FS, because the speaker's playing lower frequencies for longer on gentler slopes, if that makes sense. So 3 times if you're using 12 dB slopes, 3.5 times if you're using 6 dB slopes. And these are just a guide. For mids, they're not as sensitive to excursion as tweeters, but you still need to protect them from over excursion. They generally don't have huge Xmax values for mid-range speakers, so you want to be kind of 2.5 times the FS. To give you an example, let's say I have a mid-range with an FS of 105. That means the absolute minimum I would want across them is probably 210. To be safe, I'd probably aim for a crossover of 230, 240, 250, something like that. And to kind of give you an example, let's say that, and I'm making these numbers up, let's say my excursion at 250 hertz was 1 millimeter, and I had an Xmax on this speaker of 5 millimeters. By the time I'm playing down at 160 hertz, right, if I was playing the speaker at 160 hertz, I would be looking for 4 to 5 times the excursion. So that would be, I want the speaker to be moving 4 or 5 millimeters compared to what it would be at 250, right? And this is the problem with playing your speakers low as they are, so 160 is still a long way from 105, but as you go down in frequency, the multiplier in terms of the excursion that you need from the speaker to play that frequency at a SPL level that's equivalent, ramps up exponentially, right? So yeah, you've got to be careful about crossing your speakers low when it comes to mid-range, right? If you want a speaker to cross low as a mid-range, then you need a bigger speaker, like maybe a 4-inch, or so. Check out the FS values, and if you've got a bigger Xmax, well then of course you can play a little bit lower. If you've got a stiffer suspension, you can play a little bit lower, but two times FS is the standard safety margin. Alright, so next is the mid bass. Now they're even more forgiving than the mids, but you still need a safety margin for mid bass. I've put in 1.5 just to be conservative, but that's maybe 1.2, something like that. They're certainly more forgiving, but it's not correct to say that you don't need a safety margin for mid bass because of all of these issues here with more distortion and excursion on your speakers and them being less controlled. So a bit like sort of going over the Xmax limit, you can kind of do it, but you'll pay for it in terms of sound quality. Now, and then there are subs. Now, subs are the most forgiving of all. You can pretty much cross them down to the FS, maybe even a bit lower. Once again, it will affect the quality of the sound. But they're a little bit more robust, and you just got to be careful with the power, particularly if you're running soft suspension subs, because you can cause over excursion, and then a bit like Xmech, you can damage or destroy your subwoofers. Okay, so that's a bit of a rundown about FS, what it is. All of those types of things, and how you can apply safety margins to keep your speakers away from dangerous over excursion. Okay, so with that said, we're now going to move on and take a look at how FS works in different installations. So far we've been talking about speakers mounted in free air, just on mounting rings, venting into a door void or into a dash, or speakers set up in IB. But how do things change when we put speakers into a sealed box or a ported box? Well, first of all, the terminology that we use, the shorthand that we use changes. So FS stands for resonant frequency in free air. S is free air. When we change to a sealed box, then we use the term resonant frequency in a sealed box, which is FC. So whenever you see the little symbol C, it means a sealed box, and in a ported box, the little symbol is B. So, when you're looking at the tech data sheets or something about your speakers and it talks about FC, then they're talking about a sealed box, right? So what's different between free air and a sealed box? Well, as we talked about earlier, we have air that in a sealed box can't escape, can be compressed. Now in a ported box it can escape, but it releases pressure at a certain rate based on the size of the port. But look, I'm not going to get into ported boxes because that's a whole nother technical level that I really don't want to spend during this tutorial. So we're just going to talk about sealed boxes for the moment. But when the air is trapped in a sealed box, then there's a certain level of compression, as we talked about before, and it acts like an air spring, right? And that obviously is the amount of air spring is determined by the kind of size of the box. But when you look at free air, we have the electrical dampening, the back EMF, and we have the suspension and cone suspension and cone flex losses and the friction. On the mechanical side, to give us a total QTS. QTC is similar. So the the electrical damping is the same, but the mechanical dampening now includes this air spring, or this acoustic dampening as we call it, right? And so QTC will be different to QTS. And this shows up when we're talking about the resonant frequency, right? So let's say we have a resonant frequency in free air of 70 Hertz, right? When you put the speaker in a sealed box, the resonant frequency will go up. And that's because we've got extra stiffness in the suspension because of this air spring, right? So your resonant frequency will go from 70 to 75, or 80 is just illustration purposes, but the key takeaway is the FS will move up. So FC will always be greater than FS. All right, so what about if you put the speaker in a box that is too big or too small for the speaker's design, right? Because we want to get the best response from our speaker, right? So we want it to be put in a box of the correct size. Well, if it's in a box that's too big, then the effect of the air spring is either greatly reduced, or if the box is super big, then it will act like it's in free air. But generally, it's a bit like having a soft suspension. All those kind of things apply. The speaker will have less control over the cone. You get greater excursion, which means deeper bass and less punch. You'll have more chance of over excursion, and all of the usual stuff that happens when you've got less stiffness in the suspension, right? Because effectively we're reducing the impact of that air spring. And I'm talking about all things being equal here, right? When you're just comparing a speaker in free air versus a speaker in a big box, not much will change because the air spring is greatly reduced. Now, if you put in a box that is smaller than you need, then the opposite is true. You'll get more of an air spring impact, more control over the cone. It takes more power to drive it. Less deep bass because you can't. The excursion on the cone is not as great as on the softer, less controlled speaker. It'll be more punchy, but can be a lot more peaky, right? So, yeah, that's the effect of having it in an oversized box or an undersized box, right? So, how do we actually work out the correct size box that we need for a particular speaker? Well, I promised earlier that I would go through it, and now's the time. So this is the formula that we're going to use. It is QTC, so the resonant frequency in a sealed box, which will use the resonant frequency in sealed air, the speaker's QTS. We're going to use the VAS number, which is, if you remember, the VAS number is the volume of the air that has the same springiness as the speaker's suspension, right? As we said before, we use that in box calculations, and so here we are. And then we're going to have the box volume, right? The internal box volume, excluding the speaker, excluding any internal bracings, just the box volume in cubic feet or in litres or whatever units that you're working in. So that's all fine. What we're going to do though is actually pick a target quality or target dampening level, right? So 0.707, QTC of 707 is balanced. If you want lower bass, aim for a lower QTC target. If you want punchier bass, then aim for a slightly higher target. If you need the smallest box possible, then go for a space saver. So the lower the QTC target, the larger this box volume is going to come out at. So if you want a smaller box, then aim for a higher QTC value, but just be aware it's going to be more punchy, and the bass won't be as low, right? So it really depends on what you're looking for, what you're going to choose, but most people would choose 0.707. So we need to rearrange the formula so that we can solve the box volume, and so we do that. So the box volume equals VAS VAS times QTS squared, and it's going to be QTC squared minus QTS squared, right? So yeah, okay, so now we're going to do some maths. And so if we just plug in all of those values, we end up with 40 times 0.185, 0.5 minus 0.185, and that ends up giving us a number of 23.5 litres. So that is the size enclosure that you need, internal volume that you need in an enclosure to give you a balanced playing subwoofer or mid bass or whatever it is that you're building, right? Now, if you chose a lower QTC value to aim for, then this number might be higher. It might be 32, and if you chose a higher QTC number, it's a bit punchier with, I guess, a higher low end. This might be 21 litres or 19 litres or something. I'm not sure. But the thing is that this box volume will change depending on your target QTC. Okay, well, the next topic is sensitivity, and the shorthand for sensitivity in the technical data sheets is usually SENS, or it might be just written as SPL, because sensitivity is basically how loud a speaker will be for a given amount of power, right? So sometimes that's why they call it SPL, because sensitivity and loudness are kind of the same thing. So the way that sensitivity is measured is you take a speaker, you place a microphone 1 meter away, and then you put 1 watt of power into the speaker, and then you measure how loud the speaker plays in decibels, right? And that is the measure of sensitivity. So you'll end up with so many decibels per meter per watt. So you can take, so as long as you don't change the distances or things or the power going to the speaker, you can measure different sensitivities of different speakers. So I can put a different speaker in there, and I get a decibel level. And then what that means is I can then compare two speakers to determine how loud they will be with the same amount of energy at the same distance from the microphone, and I can do some comparison stuff. So let's say with speaker 1 I got 89 dB, with speaker 2 I got 86 dB. That would tell me that speaker 1 is more sensitive than speaker 2, and what this means, doesn't seem to be a lot, but let me show you that a 3 dB increase in SPL is 2 times the power, right, or a doubling of the power. So that means if I was feeding 50 watts into speaker 1, speaker 2 would need double the power, or 100 watts, to make the same level of output. And that's quite significant. So that's, whenever you see a 3 dB rise, that's a doubling in power. So the big takeaway about sensitivity is sensitive speakers beat bigger amps. They make more volume from less power. And we'll see how that works in just a moment. Now, one of the things I just want to make you aware of is some manufacturers list their sensitivity measurements, instead of being 1 watt per meter, they list it as 2.38 volts per meter. Now, the reason that they do this is it goes back to the old days of home audio speakers, right? And 2.83 volts into an 8 ohm speaker is 1 watt, right? And so if you're measuring an 8 ohm speaker, then this measurement and where is it? This one here. This measurement is the same, because at 8 ohms, 1 watt is equal to 2.83 volts, right? So same, just using different units of measure. But when you're putting 2.83 volts into a 4 ohm speaker, then now we're putting 2 watts in there. And so 2 watts would actually give us 92 decibels. So they would list this speaker in the specifications as a 92 dB sensitive speaker at 1 meter by 2.83 volts. Now, because it's a 4 ohm speaker, it looks better than it really is when you use the standard 1 watt 1 meter rule or version that we tend to use as a standard. So this is a tricky way that manufacturers can artificially inflate the sensitivity levels of their, well, how the sensitivity looks on the technical data sheets if you're not aware of this difference in volts versus watts. And it gets worse if you go to a 2 ohm speaker, because 2.83 volts into a 2 ohm speaker is actually 4 watts. So now this 89 dB sensitive speaker is now 95 decibels, or looks to be 95 decibels. Now, the speaker hasn't changed. It's still just as sensitive. You're just getting a better result because you're putting the same amount of volts into a speaker with lower impedance. Yeah. So just make you guys aware of that. Just be careful that you don't sort of get caught out by looking at something that is in volts instead of watts. All right. So back to sensitivity. What is a sensitive and an insensitive speaker? Okay. So here is typical car audio speakers. They'll typically range from the low 80s to the high 90s. So if you see something that's like 101 sensitivity, or I don't think I've ever come across anything sort of higher than about 96, but be wary if somebody's got ridiculously high sensitivity levels, or they don't put the units right, because it's probably because they're measuring in this 2.83 volt thing that I was just talking to you about. But cut a long story short, speakers above 90 are sensitive to very sensitive. Speakers 87, 86 are kind of average, and when you're getting into the low 80s, they're quite an insensitive speaker. What that means is you're going to need to put more power into insensitive speakers to get the volume out of them, right? And to kind of explain that, let's just work out how many watts of power you would need to produce 96 dB, right? So a 96 dB sensitive speaker would just require 1 watt, and it would produce 96 dB, right? That's 1 watt in, 96 dB. That's what that's what this 1 watt per meter means, right? So 93, then I'm going to need 2 watts because it's 3 dB less. I need double the power. Double the power from 1 watt is 2. If I 3 dB down at 90, now I need 4 watts. Another 3 dB down, now I need 8 watts. So by the time you get to an 81 watt sensitivity speaker, you need 32 watts of power, or 32 times the power, to make the same level of output as a 96 sensitivity speaker. Now, we can work out by looking at the sensitivity of the speaker just how many decibels it will play given the amount of power you put in, because loudness is a function of sensitivity plus how many watts that you're putting into the speaker. It's going to be louder if you put in, let's say, 100 watts versus 10 watts, right? That only makes common sense. So the formula for how to calculate how loud a speaker will play is loudness equals the sensitivity of the speaker with 10 times log to the 10 of the watts that you're putting in, right? So how do you figure out this? We'll just pop it into a calculator and it will tell you, right? So let's say a loudness, we want to know the loudness of a speaker. We want to put in the speaker sensitivity. We want to put in the number of watts that we're going to be supplying that speaker. And, so let's say we have an 81 decibel sensitivity speaker, very insensitive, and I want to put 30 watts in it. How many, how loud would that play when I give it 30 watts? Well, it's 81. This would be, log 10 to 30 is 1.48. 10 times that gives you 14.8. So I now need to add 81 and 14 together, which gives me a grand total of 95.8 decibels. So for 30 watts, I'm going to get the 81 sensitivity speaker is going to give me nearly 96 decibels of output. So let's do that for all of these speakers on our little table. So here's the 81 sensitivity speaker. It's going to produce 96. When I get a 90 sensitivity speaker, I'm going to be producing 105 decibels, and a 96 sensitive speaker is going to be producing 111 decibels. Now remember, this is not a linear scale, this is logarithmic, so for every 10 dB that's a doubling in volume, right? So 96 to 105 is almost 10 dB, that's double, right? This speaker is going to play twice as loud on 30 watts as this speaker, and then by the time you get to this speaker it's going to be playing another, not quite double again, but another 50% louder, right? So, this 15 dB is going to be 2.5 times louder than this this 96 dB sensitivity speaker is going to be 2.5 times as loud as the 81 dB speaker. And that's pretty loud, right? Yeah. So I guess some takeaways, right? Some things you need to know about sensitive speakers, why they matter. And so the first thing is sensitive speakers matter more than watts. A speaker's sensitivity is more important than whether it's a 200 watt speaker or a 400 watt speaker. Always go for a more sensitive speaker. And the reason for that is, as we just said, a 93 decibel sensitive speaker with 30 watts will produce 108 decibels. If your sensitivity of your speaker is 87, you need 126 watts of power just to match that 108 dB, right? So it's not a big difference in sensitivity, but you need to put a lot more power in to get the same output. So sensitivity, you'll get more loudness for bang for your buck with a sensitive speaker than you will with big wattages. The second one is, we touched on this before, is that every 3 dB of difference in sensitivity is a doubling in power, right? So, once again, a 93 decibel sensitivity speaker, a 87 dB sensitivity speaker needs 4 times the power just to come out and play the same output as this speaker here, right? I mean, that's a massive difference. And then sensitive speakers, you can run smaller amps. They need less power than insensitive speakers. They run cooler, so they physically have less heat, which means that they have more thermal. You have higher thermal limits, right? Because they play obviously louder with more power. So there's lots of advantages to sensitive speakers. So what do you look for beyond just the sensitivity metric in the data sheet? And usually you'll be looking for something in a speaker that has a high motor strength, a large cone area, and a small moving mass, right? They're the characteristics of sensitive speakers. So there you go. That's my tip of the day. So while we're on the topic of sensitivity, I'm going to talk about efficiency. So how much power supplied to the speaker is actually turned into sound energy. Now, a lot of people aren't aware that, they think that they put 100 watts of electrical power into a speaker, that somehow it produces 100 watts of acoustical energy. That's not the case. In fact, 98% of the power that you put into a speaker is actually turned into heat. So only a very small percentage of it is actually turned into sound energy. Now, I cover this topic in depth in the tutorial called How to Make an SQ System Loud. If you're interested in that type of stuff, feel free to go and check that back out. So how do you work out how efficient a speaker is? Well, manufacturers don't usually publish efficiency data on their technical data sheets because efficiency is hard to measure and it's frequency dependent and a whole bunch of other stuff. So efficiency and sensitivity are kind of the same thing because more loudness per watts means the speaker is converting more power to sound, which is basically efficiency, right? But as a rough guide, the smaller the speaker, the more efficient they are. So tweeters generally, convert 2 to 3% of the power that you give them into acoustic energy. Mids somewhere between 1 and 2. Mid bass, 0.3 to 1. Subs are even worse, 0.1 to 0.5. Yeah, so surprisingly, up to 99.99.9% of the energy supplied to your speaker can be lost in heat. So yeah, that's speaker efficiency. So I have two speakers. One is 500 watts, one is 350 watts. And if I ask you which of these speakers would play louder, most people would choose the 500 watt speaker. But it might surprise you to know that it's actually the 350 watt speaker which is the louder of these two speakers. And a lot of people would automatically say, well, but socket, how can that be? And the reason for that is the wattage on a speaker is not a measure of its loudness; it's a measure of its power handling capacity. So yes, a 500 watt speaker will handle more power than a 350 watt speaker. In fact, wattage is on a speaker is how much continuous electrical power can a speaker handle without being damaged. Now, we also need to be a little bit careful because there are different or two different types of wattage that you will find in the technical data sheets or on the back of the back of the cone of a speaker or something, and that is RMS or root mean squared power, which is basically the average continuous power that a speaker can handle. It's like the everyday, running of the speaker, right? And then you have what they call peak power, which is really just the power limit that the speaker can handle in extremely short bursts. So you might have a speaker that has RMS of 350 watts and a peak power of 1,000 watts, right? Now, speaker manufacturers love to, put big numbers on the peak power, but to be honest, it's not necessarily a value that is very useful because you can't run your speaker at that peak power rate, right? Yeah, that's why it's called peak. So when you're looking at the wattages and the power handling capacity of a speaker, make sure that you're looking at the average or the RMS continuous power number. Okay, so when you're talking to an electrical engineer, the definition of watts is actually the rate of power used or transmitted, where 1 watt equals 1 joule per second. So if I'm using my 300 watt toaster to cook toast for my breakfast, that toaster is using 300 joules per second, and yeah, that's the rate of power that toaster would be using, right? But we also talked about watts earlier in the tutorial when we were looking at how a speaker works and how the voltage, and the current sort of moves back and forward in different directions through the voice coil. And the formula is for calculating watts at any particular time is volts times current, which is measured in amps. Now, the other thing that people often get a little confused about is if I have a 100 watt speaker, does that mean it's drawing 100 watts of power from the amplifier? And it doesn't really work that way. A speaker is a passive device. It doesn't have any electronics to pull stuff from, or draw power from something. It's actually the power is delivered to the speaker, and so the way that how much power is being delivered to a speaker at a particular time depends on the volume or the input signal level to the amplifier. So as you turn the volume up, the input signal to the amplifier gets bigger. The amplifier responds by increasing the voltage, and the voltage the impedance of the speaker determines how much current is let through, and if you multiply the voltage that the amplifier is generating plus the current that is running through the speakers because of impedance, then you end up with the watts that are being delivered to the speaker at that particular point in time. And of course, the wattage to the speaker is always going up and down. So, if you're running your system and you're listening to it daily, it's unlikely that you'll be sending a full 100 watts to the speaker. That'll be super loud. It's probably more like 20 or 30 or 40 watts, for example. It really depends on the loudness and the impedance of your speakers. Okay, so now that we've covered off, I guess the major concepts around speaker wattage, let's go back to our original example where we had the two speakers, one at 500 watts and one at 300 watts. So these are our two candidates. We have candidate 6MR500-NDY-4 and our other candidate is HCCA62N. Yeah, like all good speakers, they have an alphanumeric name, but I'm just going to refer to them as speaker A and speaker B, right? So here is the technical sheets for specifications for both speakers, and of course the first thing we're going to look for is their power handling, right? So speaker A can handle 500 watts on average RMS and 1000 watts peak. Speaker B can handle 350 watts average RMS and 1400 watts peak. So just looking at these two, just looking at the RMS, you would say, well, this would be the loudest speaker, right? But as we know, and we saw earlier, that loudness of a speaker is more related to its sensitivity than how many watts it can handle, right? So if I look at the sensitivity for both of these speakers, this one has a sensitivity, speaker B has a sensitivity of 99, which is extremely sensitive, whereas the other speaker has a sensitivity of 96. So that's interesting. So just based on sensitivity, there's a 3 dB difference, which would mean that to play the same loudness, this speaker would need twice the power, right, to match this speaker. So let's say we were using 100 watts of power into both of these speakers. We can do a quick calculation, which is 10 times log of 100 watts is 20, and add that to the sensitivity. So we've now got 116 dB for this speaker and 119 for this speaker. So this is 3 dB louder than this one, right, at 100 watts. Okay, so far so good, but that's not the end of the story. It also depends on your amplifier and how much power it can supply, and whether it's stable at 1 ohm or 2 ohms or 4 ohms. So let's say, for example, I have an amplifier that is stable at or can provide 300 watts at 4 ohms and 500 watts at 2 ohms. And I'm just making this up. This is some magical amplifier, right? So once again, if I go and take a look at the data sheets, what it tells me is that speaker A is a 4 ohm speaker and speaker B is a 2 ohm speaker. Now, the impedance of a speaker, whether it's 2 ohms or 4 ohms, doesn't make it automatically louder. What it does allow is a 2 ohm speaker is less resistant to the current passing through the speaker. So if the amplifier is able to, the amplifier will deliver more power. So yeah, if that kind of makes sense. So for this amplifier speaker combination, speaker A would only be getting 300 watts into the speaker because it's a 4 ohm speaker, right? And at its maximum level, the maximum sound decibels it will make is 121. Right, 300 watts, blah blah blah, 25 plus 96 is 121 dB, because the amplifier can only deliver in 300 watts. And for this 2 ohm speaker, the amplifier can provide 500 watts. So that comes out to be 126 dB. So a good 5 dB. Now, if every 10 dB is a doubling in sound, so 5 dB is pretty significant, right? So why is this one the louder speaker? Well, it's not because it has 350 watts of RMS. It's a combination of the sensitivity, it's a combination of the amp that it's paired with, and whether that amp is stable at 2 ohms and how much power it can deliver at 2 ohms, right? So looking at the loudness of a speaker, yeah, is a little more complicated than just looking at the wattage on the back of the pack. Alright, let's take a look at frequency. So as you already know, the range of human hearing is between 20 and 20,000 hertz. So a hertz is 1 cycle per second. So at 20 hertz, that means the speaker cone is moving in and out 20 times a second. And at 20,000 hertz, it's moving in and out 20,000 times a second, which is incredibly fast. So in car audio, we use different speakers to play different parts of the sound spectrum, right? So subs to play, the low bass, and tweeters to play the very high frequencies. And of course, when we're doing our tuning, we use crossovers to limit the frequency range the different speakers play, and we allow a certain amount of overlap so that there's a transition between, for example, the tweeters and the mids. We have this thing called a crossover region. So you guys are kind of all familiar with that stuff. But if I overlay the speaker sizes, across this frequency chart, you'll notice that at the high frequencies we use very small speakers, 1 inch, 2 inch, and down at the very low end we use very large speakers, 10, 12 or 15 inch subwoofers, right? But why is that? And the answer to that is because different frequencies have different wavelengths, right? So a wavelength is nothing more than the sine wave of a particular frequency, completing its 360-degree phase cycle, is 1 hertz, and at 20 hertz, right, at that particular note, this distance or this sine wave or sound wave is wavelength, I should say, is 17 meters long, right? It's huge. At 300 hertz, it's 1 meter. At 3000 hertz, it's about 10 centimeters. And at 20,000 hertz, it's about 2 centimeters, right? So very, very small wavelengths at this end, very large wavelengths at the low frequencies, right? Fantastic. So, but what's that all got to do with different speakers? And the short answer is, when we look at speakers that we need for high frequencies, we want them to be able to create very fast, tiny movements, because they're going to move back and forth, thousands of times per second, right? So very, very small movements. They're not going to move a lot of air. They're moving very, very quickly. And therefore you only need a very tiny cone, very little excursion, very little power, and they produce very little heat, right? So that's the characteristics of tweeters or speakers that play very high frequencies. Whereas down at the other end of the scale, the lower we go in frequency, the slower and the bigger the movements need to be. We need the cone to move more air per stroke, which means that we need bigger cone area and bigger excursion. And because we've got more mass in the cone and we want to move it further on each stroke, that means we need more electrical power. More power means more heat, which means more cooling. So, as we go from high frequencies to low frequencies, the amount of air we need to move, the size of the cone and the mass of the cone, the power needs and the heat generated all increase as you go from high frequencies to low frequencies, right? But why can't we just have one speaker that can play the entire range? And the answer to that is because speakers have limits, right? All speakers have a high frequency limit and a low frequency limit. Now, there are speakers called widebands where this, this usable frequency is very, wide, but even so, all speakers have these high and low limits. So let me explain what these limits are and how they kind of work. Okay, let's say that we have a 6.5 inch and a 3 inch speaker and we want it to play 1000 hertz. Now, at 1000 hertz, we want the speaker to move back and forth 1,000 times a second. And so if you think about it, 6.5 inch speaker has a big cone and a big excursion, it can move back and forth with big strokes. So getting this speaker to move back and forth 1,000 times a second means the motor has to push all of this weight, make it brake, make it sort of reverse direction very, very quickly. And so it's got a big throw. It's going to be difficult to move back and forth quickly, whereas the little 3-inch with its much smaller cone and its much smaller excursion, maybe it's 4 mils or something like that, then this is going to be able to move back and forth much easier than this big 6.5-inch, right? And so if we want to play 1,000 hertz, then the 3-inch speaker is got better design characteristics than the 6.5-inch for this particular task. So, all speakers have what we call a high frequency limit, right? That we call the cone breakup point, right? So if we think about our 6.5-inch speaker, there'll be a point where, the motor can only push it back and forth cleanly before it starts to distort and have problems, right? And that is basically the cone breakup area point, right? The 3-inch will do the same. Like if you try to play it too high, it will reach its cone breakup point as well, right? But the cone breakup point is basically where the cone is no longer in control. You're trying to accelerate it faster than it's designed to, and it starts to bend and flex. And because certain points of the cone are at different relative positions to each other, that means that you start to get distortion and phase issues and things like that. The motor is trying to accelerate and break the cone faster than it's capable of, so you start to get reduced output. And of course, as we talked about earlier, inductance rises with frequency, which means that for the same power, the voice coil is becoming more resistant to current direction changes, and therefore you get reduced output as well, right? So all of this is happening as you approach and pass this high frequency limit. And we can kind of see this in the frequency response and impedance curve when you look at your speaker technical data sheets, right? If they provide this this little plot. So in black is the frequency response. You can see that it's kind of falling off around about here. The output starts to take a huge nosedive, and that is because of the inductance, which is here in red, starts to go up. The cone acceleration, or the moving mass acceleration, starts to fall off, and the cone bends and flexes, and we start getting all this beaming and distortion and other things kind of going on. So you can kind of while it's not 100% clear on this graph, but the cone breakup point for this speaker's somewhere in this area, right? Somewhere in there. So that's what we call the high frequency limit. Okay, so let's just take our 6.5-inch and our 3-inch speaker, and this time we want it to play 100 hertz. Now 100 hertz compared to 1,000 hertz is a much lower note, and to play lower notes you have much bigger wavelengths, and therefore you need to create more acoustic energy, which means more power, moving more air with every stroke of the speaker. So what that means is if you're using more power, you're going to be generating more heat. You need more air moved per speaker stroke, but the strokes are much slower. So if you think about little 3-inch, it's going to be now moving, compared to 1,000 hertz, it's going to be moving 10 times slower. The cone area and the excursion of the speaker cone hasn't changed, however, but at some point, this little 3-inch is not going to be able to move enough air or deal with enough power to play super low notes, right? When you compare that to the 6.5-inch, which has a much bigger cone area and is able to extend further, which means it can push more air per stroke. It has a bigger motor, so it's more powerful, so it can push more air, and it's able to deal with much more heat, right? So the same way as we have a high frequency limit, we have a speaker with a low frequency limit, and in the case of low notes, when you're looking at 100 hertz, then the 6.5 is going to win because it's got bigger cone area, bigger Xmax, and a bigger motor, bigger, stronger motor that can push more air and deal with more heat, right? So between the two, this is going to be the winner to play lower notes. And it's the reason why you find that, mids and tweeters don't do hair tricks, right? Because they just simply can't move enough air. So this lower limit, right, is what we refer to as the Xmax. You can push your speaker beyond that, but we're going to get, once again, declining sound quality and distortion and things, and lower outputs. And yeah, so what's happening here? Well, first of all, the cone is reaching its excursion limit, right? So the ability of the cone to move the air needed to play a low note, there's a physical limit of that, right? The little 3-inch can only move so far, right, and push so much air per stroke. And so you hit that limit, and if you try to keep pushing, you just get less and less output, right? And to move all of that air, you need more power. More power means more heat. So the more you try to push it, the more heat you generate, and eventually you end up with thermal failure, right? The adhesives in the speaker start to melt, or the voice coil burns out and fuses, or whatever. And we kind of looked at this a little earlier when we talked about Xmax and Xmech, right? So yeah. But once again, when you look at the frequency response graph and the impedance curve, you can kind of see, you can kind of see where that point where the speaker starts to enter this area and the output starts to drop off, right? So in a nutshell, all speakers have a low frequency limit and a high frequency limit, right? There's a point where they can't play notes any lower because they run out of excursion, or they start to hit their thermal limit, right? They can't handle the power that's required to play that note at a particular frequency. And at the other end, they reach a limit where they can't oscillate any faster to produce a high frequency note, right? They get to a point where the cone starts to break up, and the impedance and that type of thing starts to reduce the output of the speaker, right? So there's this usable frequency range that all speakers have, and it's called the pistonic zone because the cone is working as a piston. It's nice and smooth, it moves back and forth, and it's basically where the speaker is operating within its thermal and mechanical limits, and therefore you get the best sound quality and the best loudness, right? So when we're doing our full range measures, we can kind of see where these lower and upper limits kind of are. So here's a full range measure of our tweeter, and yes, we have a 1000 hertz crossover put in there to protect it from over excursion, because as you go lower, excursion increases. Tweeters have very tiny excursions. If you make the tweeter play a low note, it will cause the membrane of the tweeter to flex too far, and that's how you end up damaging your tweeters. But anyway, that aside, when we do a full range measure, we can kind of see where these upper and lower limits are, right? This is where we're asking the tweeter to play higher than it can, and you can see the output just drops off, right? Because you've reached the cone breakup area of that tweeter. It cannot vibrate any faster than it. This particular one drops off at 14,000 hertz or whatever it is, and same on the low end. It gets to a point where it can't play any lower than that because of its excursion limit, right? And the same with our mids, right? You can see here where the upper and lower limits of the mids are. It starts to fall off. And you start getting more distortion. And the same with our subs, right? It won't play lower than that, and it won't play kind of higher than that, right? So all speakers have this natural high and low frequency limits, and you can, as I said, you can see them when you're doing your full range measures. And this is the reason that we put crossovers in around about this point, to stop our speakers, to keep our speakers playing in their nice operating range, and stop them from playing outside of that operating range, if that makes sense. Okay, so I just want to talk about different speaker configurations in car audio systems. So Take a typical system like a excuse me, a three-way and a sub, so tweeters, mid-range, mid-bass, subwoofer, and they're all playing, the intended frequency range that they want to play. Now, I always say that the most important speakers in a car audio system are the mid-bass and the mid-range. They do most of the musical, heavy lifting. The tweeters add a bit of sprinkle, detail to the top end, and the sub, gives the extra boom down the bottom end. But they kind of add something to the sound stage. They're not the entire sound stage. Most of the sound stage is between these two speakers, right? So when it comes to a three-way with no sub, right? Let's get rid of that for a minute. The system will play fine. Of course, you won't have the boom boom of the low bass, but it will sound pretty good. You might even be able to push your mid bass down a little bit, right, to get it a bit lower. But without a sub, it's going to be musical. It just won't have that super boomy low end, and you just got to be careful not to try to push your mid bass down too far, because it's going to reach the excursion limit, and if you do, it's going to sound boomy and terrible and distorted, and you're just going to put your mid bass at risk of thermal damage, right? So what about a two-way system, right? Two-way system with no mid-range, so I'm going to get rid of the sub because it doesn't have one, and doesn't have a mid-range, so let's get rid of that. So this is quite popular with manufacturers that are selling component systems and people that want to run a two-way system with no speakers. So they'll often have the mid-range playing way up here, and they'll have the tweeter playing, way down low to try to meet it. Now, I'm personally not a big fan of that. I much prefer three-way systems, and the reason for it, as we just said, right, this mid-bass will play 1,000, 2,000 hertz, whatever it is that the crossover is going to be, but is it going to be as clean and as nice as if it was being played by a speaker that is the right size to play it? Now, I know you can buy component systems where the mid-bass and the tweeter, are paired, to do this. And yes, as I said, it will play, but will it play it as nicely as if you had a mid-range, right? Maybe not. So often people come to me for help with their two-way systems, and because they'll have a huge dip in the middle here somewhere, right, where the mid-bass and the tweeter are struggling to cross over properly, and I see that quite commonly. So is there a problem with running a two-way system like this? No, absolutely not. If you're pressed for space, or you don't have enough channels on your DSP, or for whatever reason you want a two-way system, then certainly nothing wrong with it. In fact, if you buy a component system where these things are supposed to be matched together, then provided that everything is installed properly, they should cross over. Just be aware that while they can play like this, doesn't mean that they play this region particularly well. All right, let's move on. So two-way with a sub and no tweeters, right? So what would that look like? So we'd have our sub, we'd have our tweeters, don't exist. It would typically mean that we try to get our mid-range to play a bit higher, and maybe have our mid-bass play a little bit higher, but not always. No, let's not do that. Let's just put that back. Let's say we do that, boom, like this. Now, often, once again, the problem is that you'll have all this end of the spectrum is fine. Of course, we won't have the super sparkly, tweedy details. You might get this to play up to 6,000, 7,000, 8,000 maybe, but you won't get that top end detail. Unless you try to push your mid-range to play way up here, which you're probably going to run out of. Cone's probably going to break up because they're not built for vibrating at 8, 9, 10,000 times a second, right? So quite often these will be wideband speakers. They'll have specs that say you can play from 50 hertz all the way to 20,000, or something like that. But same as the previous example, you they might be able to play that. Will they play them well is another question, right? So wide bands are normally, they won't be 4-inch. They're probably 3-inch or maybe even 2.5-inch, and they're a compromise, right, between a tweeter and a mid to try to get a mid-range to play super high. But once again, you can have a decent system with it. You just be aware that the top end is going to suffer, right? Okay, so they're just like some of the common systems that people might be running. Three-way system with a sub, or a three-way without a sub, or a two-way system, just mid-bass and tweeters, or maybe a system without tweeters and using a wide band, to cover that kind of top end, right? Nothing wrong with any of these systems. They just have different compromises. In my opinion, the best setup is a three-way with a sub. Just because the speakers are designed to play these specific ranges, right? They'll do it effortlessly within their proper operating band. Just pointing that stuff out. Okay, so when you're buying speakers and stuff like that, well, how do you work out what frequency range the speaker will be playing? And it's a bit tricky. You can kind of look that up on the technical data sheet. You'll have maybe the frequency response listed, and this one is 60 hertz to 5,000 hertz, right? So that's a pretty broad range. As I said, it can play it, but is it going to play it well? That, according to this spec, that is the operating range of this particular speaker. So you can either read it off the sheet. You can look at the shape of the frequency response graph and kind of eyeball it. You can look at the FS of the speaker, or maybe the you can read the FS off the over here, 2250, or look at the impedance peak. There's lots of different ways to get an indication from the technical data sheet about the frequency range that the speaker might play. Now, just bear in mind that this has all been done in a lab. And so real life and how the speaker will play in your car, depending on where you've installed it, how you've installed it, whether it's in free air or in a box, or how much breathing space there is behind it, and all of that type of stuff. It may look different. So here is a real life example. Here is the technical data sheet. Here is the plot, and here is the actual measurement of the tweeter, in my particular location. So this thing's kind of rolling off here at about 3,000 hertz. It's pretty close there, but you can tell that the curves are not identical, and that's just because of the way that they've been installed, right? And that changes. That kind of brings us to the end of the speaker spec tutorial. I've just pulled up a random technical data sheet, and we'll just run through it really quickly to look at the things that we covered in this tutorial. So power handling, yes, we talked about watts. Impedance, Z, which is the amount of resistance that the voice coil has to power, how many ohms of resistance it has. DC resistance, which is the voice coil. Frequency response, we just talked about. The resonant frequency FS, that's the point where the suspension and the moving mass inertia balance out, and that's where the cone excursion is maximum because it's so easy to move. The QMS, QES and QTS, the dampening factors, right? That dictates how the speaker is going to behave at that FS, whether it's going to be tall and peaky because the suspension is very soft, or short and controlled because the suspension is very stiff. And then compliance, which is the speaker CMS, that is the speaker's suspension compliance, how stiff it is, and that we talked about stiff speakers are better in sealed boxes, soft speakers are better in free air, so the CMS is a good indication of that, but we often use QTS to work that out. Equivalent air volume, the VAS of a speaker, is not the size of the box that you need for your speaker. It is the air spring equivalent to the springiness of your speaker suspension. Then we had force factor, or BL, which is the motor strength of the speaker, how hard or how much force it pushes the speaker cone with for a given amount of power. Sensitivity, so how much loudness will it produce with 1 watt. And they've also, this company has also listed the 2.83 volts per meter spec, if you remember that. And you can see one is higher than the other because this is a 3 ohm speaker, not an 8 ohm speaker that we talked about when we spoke about sensitivity. Then we have cone area, SD, so the actual effective cone area that actually makes the noise, which is different to its nominal cone area being a 3.5 inch or 6.5 inch or something. The weight of the moving mass, so the cone, the suspension, the voice coil. Then there's a little bit of stuff here about the mechanical resistance. So this is the amount of resistance caused by friction and flexing of the spider and the surround. Then we've got things about the voice coil, its diameter, the winding, how high the voice coil is. This one doesn't have anything about the gap, because with that information we could work out how much wire is in the gap at any time. Or it doesn't have anything about magnetic flux either, so that's all kind of missing. We've got excursion, so Xmax, which is the linear excursion here, is 2.5. Xmech is 3.5. Now they've used different terms here, but that's what they are: linear excursion and maximum or mechanical excursion. Then we've got some details about the size of the dimensions of the speaker, which we didn't really cover because I think that stuff is common sense. And then of course this one has a neodymium magnet. So you know, when we run our eye down this speaker specification sheet, we've pretty much, well, we have covered them all, right? So yeah, there you go. So guys, I hope that when you're able to pull up a technical data sheet, you'll be able to read these things, know what they are, and be able to compare different speakers of the same size class, and you know, use them to do an apples to apples comparison. So that brings us to the end of today's tutorial on speaker specifications. Now, one of the things I didn't talk about much during the tutorial is, well, what does this mean for, you know, when you're comparing different speakers for an installation in your car? And the reason for that is because I'm going to cover all of that stuff in the next tutorial, which will be called speaker selection. So we'll be looking at things like QTS and VAS and, you know, other specifications when you're trying to decide, well, what is the best speaker for my door enclosure and stuff like that. So look out for that next tutorial in the series. Now, if you're interested in this kind of topic, I've got another couple of tutorials that might be of interest to you. One is called The Language of Sound, where we basically cover what sound is, phase, and all of that type of technical stuff. And then another tutorial called How to Make an SQ System Loud, where I cover things like decibels and acoustic energy and, you know, all of that stuff around the technical stuff around loudness. But yeah, if you're interested, you know, feel free to jump back and check those out. So guys, as always, thank you so much for watching. If you've got any questions, feel free to throw them down below. I will try to get to them as soon as I possibly can. Otherwise, I will catch you in the next episode.